I request everyone to kindly settle down as we'll be starting the event soon. And few quick announcements. Food is not allowed inside the auditorium, so kindly refrain from throwing any wrappers or water bottles inside the auditorium. If you have any trash, please pick it up and throw it outside. Kindly refer to the website for the agenda for today. And we'll be starting the event shortly. Thank you. A very good morning to all the dignitaries, director, professors, sponsors, organizers, and the participants of today. It is an absolute privilege to welcome you all to the third edition of the Digital India RISC-V Symposium. We are truly delighted to see a vibrant gathering of brilliant minds joining us today. I am Ananya.
And I'm Sridevi.
And we are honored to be your hosts for today. The Digital India RISC-V Symposium has grown into a cornerstone for India's semiconductor ambitions, serving as a catalyst for academia and industry. Today, we stand at the intersection where bold ideas in processor design are transformed into real-world solutions that will shape the future of our digital ecosystem. Whether you're a researcher, a developer, or an industry pioneer, today is about harnessing the power of collective intelligence to push the boundaries of what is possible.
We would like to extend a heartfelt thank you to our esteemed dignitaries, sponsors, and audience for gracing this occasion with their presence. To formally commence this milestone event, we invite our esteemed guests of honor to join us on the stage for the traditional lamp lighting.
To begin this auspicious occasion, I cordially invite our beloved director, Dr. Kamakoti Veernathan, to light the lamp.
We request our guests of honor to come on stage to light the lamp with Kamakoti, sir. We are honored to invite Dr. Kamaljit Singh to grace the stage and light the lamp. Okay. We request Sri Gokul V. Subramaniam to join the stage and light the lamp. We invite our Professor Gopalakrishnan Srinivasan to now light the lamp. And we also request Nitya ma'am to join and light the lamp.
We'd also like to have Chitra Hariharan ma'am to join us on the stage for the lamp lighting.
We now request Professor Patanjali sir to light the lamp. Ready? No. We'll come and then. We request our director to welcome Dr. Kamaljit Singh with bouquet. We request Professor Gopal to welcome Sri Gokul V. Subramaniam with bouquet. Thank you, dignitaries. We now request you to kindly take your seats on the dais.
He's going to wear shoes.
Oh, I see.
Thank you, dignitaries, once again. As we settle into the day, we are eager to begin our exploration of the architectural advancements that define our theme. I now invite Dr. Gopalakrishnan Srinivasan, Assistant Professor, Department of Computer Science and Technology, IIT Madras, to deliver the welcome address.
Am I audible on the mic? Is it better? Yeah? Oh. Is it better now? Okay. Namaskaram, Vanakkam to all the dignitaries here, from our director, our esteemed chief guests, our student, our staff, and students all over, hopefully India, because we try to run a pan-India conference here. And hearty welcome to IIT Madras Research Park, and to our Shakti family. Hopefully you'll have a wonderful couple of days with the events that we have planned. So once again, a hearty welcome to all of you to Chennai. Vanakkam, Vango. So I want to give a brief overview on what we have achieved in the last 1 year and what is our charter as we run this RISC-V Knowledge Center of Excellence, funded by the Ministry of Electronics and Information Technology, MeitY. So of course it was brainchild of Professor Padma Shri, Kama sir we call him fondly, that the knowledge shouldn't be restricted only within IIT Madras. It has to propagate to the lengths and breadths of our country. It was with that intent that we started this RISC-V Knowledge Center of Excellence, and we have really grown leaps and bounds. So we have broadly 3 charters that we try to do as a part of this center. One, of course, it is Saraswati, as Kama sir likes to say, it is to propagate knowledge. So we do conduct workshops, training programs, certificate programs, and also work with students across universities in India on our Shakti-based hardware and software ecosystem. So in this past 1 year, we have had similar training programs, certificate courses we conducted with CEG, College of Engineering, Gindi, some more universities in India also. And of course, this time we were able to take this little global. We ran a Shakti-based RISC-V program where our friends in Malaysia wanted to see what it takes to recreate like an ecosystem that we have championed in IIT Madras for India here. So we were able to educate a cohort from Malaysia, and in addition we have the mini DIR-V workshop a couple of months back. So we have trained, of course, barring the 1,000 students who gathered here, we have trained 500, 600. Hopefully they'll be ambassadors like many of you for this Indian semiconductor ecosystem. So I think that's a big part of what we do, and we will continue doing that, being an academic partner here. And the second aspect that we do is to stay on top of the RISC-V hardware and software ecosystem. So this past year, our team, so whenever I say something, I use we or our team, it's our entire Shakti group put together, who have been with us for over 10, 15 years, something more also right now. So we did a very successful tape out, and with a strategic government organization, which will be soon announced, where we have taped out one of our premier Shakti cores in an effort to, and of course, architecture, design, manufacturing, tape out, software bring up, board design, everything was completely done in our lab. Of course, we taped out the chip in SEL Chandigarh 180, and that is something we feel would further strengthen our RISC-V adoption of indigenous technology in our country. And we are trying to do a tech transfer to a couple of startups, MMRFIC, Chip Spirit. These are all startups that we want to enable to really champion our RISC-V effort. And of course, right now security has become a big talking point in India. And essentially we are working with DRDO and Center for AI Research, where the mandate for both IIT Madras and the CARE DRDO is not only run a software security stack on top of commodity hardware, but rather the entire hardware and software stack should be indigenously developed. So we have been continuously engaging with them. It's very heartening to see multiple governmental organizations working together for the technology development of this nation, right? And of course, we also contributed to a tape out of our Shakti based CPU in an SoC developed by a non-governmental organization. So that gives us a lot of credibility that we are doing really commercial worthy course, right? So again, we hope the tape out happens soon. The design is tape out ready, and we hope that the actual tape out will happen soon. So this is a part where we engage with our startup and governmental and non-governmental organizations and strategic organizations to take Shakti and champion its adoption in these organizations. For domestic, of course, eventually, we want to go global also. We want to have a very competitive product, right? We don't want people to use it because it is indigenously developed, but indigenously developed from a very commercial readiness standpoint. And since we build RISC-V based SoCs, we also work on expanding our portfolio in terms of the RISC-V extensions we support. So we have been actively working for one more tape out, which we plan to do the following year. And that is going to, just like what our Shakti C class achieved in 2017, 2018, we plan to demonstrate our capability in designing a very powerful client class, out of order superscalar core, along with a machine learning accelerator, all of it combined within a single system on chip and a single Shakti SDK, to show that we are ready with a building block for what we eventually are dreaming about, building a server system. But you have to crawl before you walk. So early next year we want to tape out our powerful cores also, and that, in our opinion, will open up even more opportunities for the semiconductor ecosystem. So these are all part of the activities. Of course, we have many more planned. Of course, we want to conduct much more DIR-Vs. So hopefully I'll keep presenting very exciting updates. But these are all a sample snapshot of what or how we help champion the RISC-V adoption from a technical standpoint. And of course, promoting startups. So usually in software industry, like when you incubate a company, I think mostly the company is all by herself. But in semiconductor, interestingly, when you incubate a company, it's like baby forever until they see the light of the day. So we do engage with them continuously and make sure that our technology are sufficiently adopted. So these are all some of the projects that we have both on both the training as well as the technology development standpoint that we have tried to do over the past year. And our goal, as we said, is twofold. One, to show that we have the technology capability and know-how to architect and design and bring up very, very complex systems on chip, which are completely indigenous, of course, except the manufacturing part, which will happen soon, with support from our government as well as non-governmental partners. And the people who really do this work are our staff and really students who are the heart and soul of our lab. So essentially, the other selfish reason to organize the Digital India RISC-V Symposium is to attract students, bright students from the nook and corners of our country to eventually come and either work with us. That will be the most selfish reason. But in general, be a part of the semiconductor mission that Bharat wants to propagate. So with that, I'll kind of conclude my welcome address. And once again, hope you'll have a very exciting couple of days with a couple of panel discussions, keynote talks, and you have some food for thought in every session that you attend here. So welcome to the Digital India RISC-V Symposium version 3, and welcome. Thank you.
Thank you, sir, for your warm welcome. I request Dr. Gopalakrishnan to introduce our director, Dr. Kamakoti Virinathan, to the audience. Thank you.
So, good morning, very good morning. RISC-V needs much more enthusiasm. Thank you very much. So, respected Dr. Kamalji, friend Gokul, Gopal, all my friends here, I feel coming back home to see the great enthusiastic VLSI Janta. So, a good round of applause to all of you. It was somewhere in 2012 where Dr. Kalam came out with a very interesting statement when he was talking about Vision 2020. Vision 2020 was one of his real brainchild. And he said that and in 2020 we would like to see every one of you, every citizen, to contribute something back to the country which is concrete and not abstract. In Tamil, if you want to translate it, kada adikade edavadhu urupadiya pannu. That was the actual statement that he made. At that point, a few of us at IIT Madras, we thought, why don't we do, we were working in the area of computer architecture. And we did realize that the days are not far off, that we may be denied these technologies. We may get processors in which we know it will do what we want it to do, but for us to ensure that it does not do what we don't want it to do is going to be extremely difficult. We also envisage that there will be an IoT era that's going to come up. Lot more intelligent systems will be part of our life. And at that point we thought, let us start and do a family of microprocessors for the country. And so myself, Madhusudan, Neelgala, Arjun, we were four initial people who joined this project, and we started looking at different options. At that point, we had some choices. We had the open power from IBM, but then we did not have any funding, and we had to run it as a student project, and that needed continuity. And for us to basically understand the complete IBM power itself was a big ordeal. And then try to make architectures based out of it, make it sovereign, and then understand the entire ecosystem. We thought we need something much more clean slate. And also we were looking at a family of microprocessors, not just single one. At that point we came to know through the BlueSpec company that there is an effort that is happening in Berkeley, wherein some of the commercial processors, of course the IP of the processor was proprietary, but they also tried to make the interconnect proprietary. The bus interconnect also proprietary. That means anybody who wants to make any peripheral for any computation system are at the mercy of these companies who have to basically certify that these peripherals will work compatible with them. So at that point, I think the world realized that monopoly will kill processor. Monopoly, especially in the programming brainchild of any hardware, which is going to be the microprocessor, has to be under much more democratized manner. And in this context, Patterson and Asunovich, two great professors from Berkeley, actually started the RISC-V clean slate project. You learn a lot about RISC-V. There will also be workshops, tutorials, and also a lot of materials we have generated over a period of time. But just to give you a very short description of RISC-V, RISC-V is an instruction set architecture which is extensible. Extensible in the sense that I can add more instructions without touching the existing instruction. Without touching the existing instruction essentially means I need not go and change the encoding of these instructions. And the encoding of the instruction is, if you give a mnemonic like move, it gets translated to binary. And what it means not touching the encoding means I need not touch the compiler, I need not touch the microarchitecture, I can keep adding instructions. And this came out with a BSD license, which essentially means it is completely free, no encumbrance, nobody can sue you on this. And very importantly, the other licenses, but in this license I can do whatever I want and I need not report whatever change I have done. This fully suited the need of our country, where we can make our own architecture. We can basically make changes to it, customize it, put it on to different strategic and civilian use, and make out a good set of family of processes. And that is where we started. And so it was almost an overnight decision that we as a group sat together and decided, let us move to RISC-V and take a big challenge there. And we were very confident that with Berkeley and that time even MIT joining and BlueSpec being part of it, this one day will become successful because the intention has been very good. From 2012 onwards till 2017, we actually worked without any money, without any great support, but we had the conviction that this will become successful. So I want to place on record my deep sense of gratitude to Madhusudan, I don't know whether he has come here today, Neil Gala and Arjun, who had been part of this very wonderful journey. And 2017, we finally had the first breakthrough, where MeitY, the Ministry of Electronics and Information Technology, after several rounds of discussion and convincing them that this is indeed a worthwhile, great project for the country, was kind enough to give us around, at that point, around 12 crores of money, which roughly translated to around a couple of $1 million those days, to start actually making a better technology-ready versions of this Shakti microprocessor. Since we started with power, initially we had power as in our mind, so we named its Sanskrit and Tamil equivalent as Shakti. So that's how the Shakti was born. Friends, after that, we thought that this entire project, as IIT Madras, we need to make more and more working processor models and make it available free of cost, no licensing cost, nothing. Make it free and give it to the startup companies. So anybody who is interested in making a processor-based system on chip must immediately get access to it and very quickly should come out with designs. And they should be in a position to modify it, etc. At this point, we did not want to release code or software which is not proven. So I must place on record great sense of gratitude that time for two organizations which came forward and said that they will help us siliconize the design. And one is Intel and another is SCL. So I am very happy that the head of Intel and the head of SCL today are our chief guests. So we made the first two designs, same design, almost same design. One went to the Intel 22 nanometer PDK design at Oregon Fabs, and another 180 nanometer which came to SCL. One we call it as Rice Creek and another as Remo. So two chips. And friends, of course when we went for the Intel, everybody said, yeah, it's a good move. But when we talked about SCL and 180 nanometer and we are going to get a microprocessor of that caliber which had even floating point and many things there, booted. So one of my friends abroad told, Kama, if this chip boots, you should retire. Right? And but we made it work. It did boot, lot of challenges. And when it booted, I called him back on midnight, around 1 o'clock when it booted. When the SCL chip booted, I said, chip is working, comma is not retiring. Okay. And all the people, almost every one of us, were new to the system. We were understanding what is tape out. But at this point, one big silver lining that we've had, big support, was the language called BlueSpec. At that point of time, we did have a lot of people who came, review, started giving suggestions, etc. And they started comparing this as a high-level language versus Verilog. Verilog was more assembly. You may not get performance. You may not get people who have not done a single chip in lifetime, not written a single microarchitecture in lifetime. But did give a lot of advices to us, many times irritating. But at that point, we put our full bet on BlueSpec. That's where, academic convention. So people say, oh, academia, industry, academia write only paper and all. But we put a lot of conviction. We did realize that BlueSpec is going to be one of the best languages Goddess Saraswati has given to mankind. And thanks again, Arvind is not here, Professor Arvind of MIT. I think we should give a big round of applause to Professor Arvind, who came out with this wonderful language, which was completely, it's type sensitive. It is unpardoning to type mismatches. It doesn't even recognize an integer as a 16-bit. 16-bit is 16-bit, integer is integer. So it's very, very important. And what BlueSpec did was that there's completely no race conditions. Race conditions had come out very early in the design process. Many, many things that we miss while doing Verilog or VHDL or even the system Verilog or system C, those were very clearly highlighted at a very early stage in the BlueSpec design. And so, all the tape outs, we have done more than 4, 5 now. We are going on the 6th and 7th now. All the 5 tape outs so far have been first time success. So I want to place on record today my deep sense of gratitude to the BlueSpec. Initially, BlueSpec was a paid software, and so there were a lot of queries on who will license it, etc., etc., etc. But down the line, BlueSpec made it luck for Shakti, I must say. BlueSpec made it open source. The code is available. So now we have designs. The design can be checked. It is free for all. The compiler which compiles the design, that's also free. The source code is there. So that gives you lot more of security. Now when we started seeing such success, then we said how to take it to the next stage. And so many startup companies were floated. And the great happiness that I get personally is that today's silicon sponsor is a startup company which is based out of Shakti, Mindgrow. And what is the third one? Gold sponsor is Incor, which also grew out of Shakti. I'm very happy. And that essentially shows that the whole project has been, the whole effort has turned out to some amount of prosperity. Friends, what we have on table today is a bunch of in order and slightly out of order in-core, single-core, multi-core architectures, which is tightly monitored by the stringent conditions of BlueSpec, which will give you very quick access to processor, which will be the brain of any of these electronic systems. We are also supporting it with many peripherals. The RISC-V Knowledge Center, which is again funded by MIT as a part of the second project. We are now porting multiple operating systems, multiple versions of Linux are stable here. And we are also ensuring that the normative architectures that we release are very close to the contemporary RISC-V specifications. As the specification grow, we also have added, for example, we added hypervisor. Hypervisor is just now finalized, and we have a fully compatible hypervisor architecture now. So, net result today, any startup which wants to do a processor-based SoC, we have the system, we have the compiler, we have the software, and with minimal effort, very minimal effort, I think a processor-based SoC is possible. And that is the overall contribution of this more than a decade project. Friends, going further, INCORE, I'm sure they are going to make a presentation, are they, this time, right? So, has come out with what we call as an SoC generator, wherein you can give the specification, it just spits out very quickly, in matter of seconds today, an architecture which you can port it directly onto the FPGA with a compiler and also a bootable operating system. And this on just a click of a button. And that is what INCORE has achieved. And again, thanks to some of the rigors of BlueSpec, this has become quite possible, and they are able to give you something very, very quickly. So, microprocessor chip for you in 30 seconds or 3 minutes is not a myth. It's now a reality. Going further, we are working on trying to make the chip more and more AI friendly. We'll be adding more instruction sets. With more and more requirement of edge AI, I think these processors will now, the subsequent releases that we are going to come out, will have more accelerators that will be integral part of the chip rather than an external peripheral like the GPUs that you are seeing. And that will possibly give you a much more better bandwidth and better processing speed and a better energy conservation when compared to the current type of AI workloads and the AI architectures we are seeing. And that will be a massive effort. Going forward, the RISC-V Shakti effort will take. We will also very shortly release in public an out-of-order, a real thug out-of-order processor that can go all the way from a mobile phone to a laptop, to a workstation, and to a server. So we will be giving you such a very interesting silicon. And again, those silicon will be, those architectures will be silicon proofed. We are not just going to release it without a proof, so that many of the companies can start making such much more complex, sophisticated systems using the Shakti class of processors. And again, those will be free, no encumbrance, and that will be the contribution. Looking back now, we are 6 years away from 2020, but what Dr. Kalam wanted us to do, I think at least a part of it we have achieved. I thank the entire Shakti team and all the startups and all the other academic institutions which have started using RISC-V in their education, etc. I give a big thanks, and I must also thank the MIT because they recognized RISC-V as a national instruction set architecture, and that's how the Digital India RISC-V, the DIR-V name was coined. By that time, Mr. Rajiv Chandrasekhar was the Minister of State for MIT, and he was instrumental in coining this name. And we have gone from strength to strength. With all your support, I'm today extremely happy to see a large number of students who have come here. This is a great enthusiasm that Bharat needs today. And when we march towards Viksit Bharat 2047, as envisaged by your Honorable Prime Minister Modi ji, I think that will be a product nation, it will be a startup nation, and that products, many of them or all of them, 99.99% of them will be electronic products. And in all these electronic products, we see Shakti or its derivatives inside. Thank you very much and wish you a great 2-day symposium in front of you. Thank you.
Thank you, sir, for those inspiring words. They provide the perfect foundation for the rest of our day. As a token of our gratitude, we request Dr. Gopalakrishnan sir to felicitate Dr. Kamakoti sir with a memento.
We are now honored to welcome our guests of honor, visionaries whose leadership and technical expertise are actively shaping the future of the Indian semiconductor ecosystem. Our first guest of honor is Dr. Kamaljeet Singh, Director General of the Semiconductor Laboratory. I now request Dr. Gopalakrishnan to say a few words about our esteemed guest to the audience. I invite Kamaljeet Singh sir to present an overview of the Semiconductor Laboratory in Chandigarh.
You can start. Its ruler is IIT Madras. Most respected Padam Shri Dr. V. Kamakoti ji, Director IIT Madras, Intel President Dr. Gokul Subramaniam ji, team from IIT Madras, Shakti, faculty members, academicians, industry leaders, students, my dear friends, a very good morning to all of you. I think today we are in the era where intelligence is engineered in each and every innovation, and the chips are making scripting the grandest of achievement in our daily life. Now in this scripting of this chip, I think this country needs lot of chips because country is importing lot of chips, and what sir has already told you, for the Viksit Bharat, we need lot of innovations to be carried out. It should be indigenously carried out, and that is why the slogan which our Honorable Prime Minister has given, Jai, that is a jointness, Atmanirbharta and indigenization. I think that is a very much apt. Going with this symposium, I am very much honored and privileged to be part of this symposium today itself. The other aspect is the RISC-V, which is there and which Jai slogan, I think, aptly comes into the picture where we should have indigenized systems, indigenized processors, peripheral of this indigenized system should be bought out. And I am very much happy to note that the contemporary processors which came out along with Shakti, but Shakti is well ahead of all others. I have some slides for that also. There are multiple reasons. Not only the indigenization is one of the reasons, the jointness which we are asking about, the industry is a partner with that, academia is a partner, because this ecosystem has been created around this Shakti, I think, which is giving a tremendous boost to this type of propagating this processor to each and every corner, to the system level itself. And the third part itself is the way you are giving it to the society, the way it has been made is open, because I got lot of praise from the startups and other people that this system is fully open and I think they can use it. So further dwelling on that, because a lot of people are not knowing about the semiconductor laboratory and all. So what we have used, what we have capable of, how we are making chips for the strategic sector, because chips are now considered to be the foundational currency for national sovereignty. And for that itself, the security is the great emphasis which has been given on that. And the security aspects starts from the architecture level itself. So I think this conference itself, the symposium itself is giving a lot of emphasis on the architecture level itself, because nowadays the process is not scaling. The scaling part has stopped. I think we are not making much headway. I think just now, I think last week itself 0.5 nanometer was there, but the scaling is not making much headway. Because if you make something chip to be scaled, the chip has to talk to outside world also. So that is why the packaging comes into play a lot of role. And that is why the packaging which you are seeing, SoC, SIP packaging, MCM packaging, chiplet, now that era has also gone, because there is something like different type of heterogeneous packaging has started coming into play. And the concept which started to coming into play is system and technology co-optimization. I think whenever you're designing a system, I think this type of things also to be taken into account. The system should talk to the chip itself. Now, before I start with my what are the capabilities, I will not take much of the time. I have a small portion that what we are doing with the Shakti processor, I think some of the headways which we are making it, and we want to replace one of the critical component which our drone industry is using, that is STM32, which is manufactured from China. We want to fully replace it with Shakti processor. Some headway has been made. I think team has contributed a lot. I have one slide on that also. So SCL is a one-stop solution, which you used to have it. We have a vertical integrated facility. We are known to be integrated device manufacturer. We not only do the design, we also do the process. We also used to do ATMP type of operations. We have also screening and qualification. We are also working in the system domain. So these are all our verticals. So from 180 nanometer, we are taking 8 to 10 flavors from this foundry itself. We used to start from TRL level 1, and we used to go up to TRL level 9. So you can see from research to deployment, and not a single ISRO mission is going without SCL chips. We are the most trusted and reliable partner. More than 1 lakh chips we have supplied to the strategic sector, and there is no field failure till date. Going with this, our verticals and all, you can see there are multiple verticals which you are working on. The design is there, the fabrication is there, testing and packaging and quality assurance is there, because we are an integrated device manufacturer. Now you can see from the design part also, we are doing logic, we are doing analog, we are doing mixed signal, and recently we started RF also, because our process has got adapted to that. I will speak about that if the time permits. In the fabrication also, we are doing a lot of things in the process-wise itself. We have a 6-layer process. We can tweak the process also. We have successfully ported 1.2 micron also to 180 nanometer. It is a 6-layer process, but recently we developed 8-layer process of 180 nanometer also. In testing and packaging, I will also dwell. Recently we introduced plastic line here itself. In quality-wise, we are following all MIL standard as well as ISRO pass standard also. You can see this process portfolio. You can find it out from design services to design enablement, from process design also, as well as turnkey solution we used to provide. We are also working in 3-5 compound semiconductor. We have a small fab for that also. Even sensors domain is also one of our main portfolio. We are supplying a lot of sensors to strategic sector. And recently what we have done is we have integrated sensor and IC together as a vertical integration as well as horizontal integration. This is also one of the niche area where sensor is integrated to the IC. Next slide, please. Now, assembly and packaging, what are our capabilities? I think this is a national foundry. So you should utilize this foundry, whatever the capabilities are lying with us, so that any of the assembly and packaging, next slide, please. If you want any chip to be packaged or assembled, I think this facility is open. You can see we have around more than 5,000 square feet of the area, which is a clean room area. Our facility consists of die attach, pick and place, wire bonding. So all this multi-zone furnaces and all the requirements which a simple packaging facility used to have, we are having under one floor. Going with that outlines of the packages, we are doing a lot of things in ceramic. We are making customized packaging as well as non-customized packaging because we are working on detectors, also CCD and FTI, which is non-standard detectors. We used to provide customized solutions for the packaging also, as well as our plastic outlines also. You can see now we have fully established the plastic outlines. Just now we have replaced some ceramic dip package with plastic dip package and giving it to strategic sector after qualification also. And we are also working towards BGA packaging also. So these are our main portfolios which we are working in assembly and packaging. Next slide, please. Now, sensors and detectors, as you know, sensors are very critical portion. Whenever you're talking about IC, the IC is not alone. It is integrated with sensors. Even you say in automobile sector or either in the drone sector also. One is that IC part and sensor is a full ecosystem consists of that. So we are working in a lot of sensors, both inertial and physical sensors, because sensor needs different type of packaging approach. So we are doing TO type of packaging also, QFN type of packaging also, and non-standard type of things like gas sensors and all. Going with another detectors application also, you can see FTI and CCD type of devices also. We have also initiated the work on CMOS image sensor, where image and CMOS is integrated together. So that also need a different type of packaging approach. So all this portfolio are there at SCL. Next slide, please. Going with multi-chip module, you can see multi-chip module is one where you have lot of chips are integrated in a single module. So we used to supply regularly to ISRO for launch vehicle applications. We have also 5G accelerometer, which is along with temperature sensor and ADC. So this is also a multi-chip module. Apart from that, we have Vikram 3201 also, which is a qualified thing in ceramic. Now this is right hand side, you can find it out. This is a SIP package. I think Bell team is here itself. They are working on that to make this a reality with the packaging portion. But what we have done is, I think today the chip will be out with a COB type of package of SIP, and that is, we are giving it to one of the industry for that. As well as we are also working on NanoSat SoC. This is system on chip, which is designed by ISRO, and we fabricated it, and it is also packaged in a SIP environment. Next slide, please. Next slide. So testing and characterizations, we have all the testers available with us from mixed signal to digital tester. We have 40 gigahertz RF capabilities also. Next slide, please. So you can find it out that we have wafer level testing also. We can do lot of physical failure analysis type of mechanism also. We are also doing probe card development as well as testing interface boards are also there. So this is a full portfolio which we are working on, and any development which has to be carried out up till TRL level 8 and all, we used to pitch in, and that is why anywhere if you want ATMP support, screening qualification support, you can bank upon SCL. Next slide, please. This is RF and DC characterization. This is also one of the niche area. We are working on that. We have the full capabilities, and recently we have bought out the NAVIC chip, where both front end is also from us, designed by us, baseband processor is from ISRO. We have integrated together also, and we are also doing a lot of testing of phase shifters and SOCs also on this. Next slide, please. So this is one of the things which we have carried out. It's step by step in last 2 years itself. The NAVIC chip was there. The front end was taken out from outside. The baseband processor was from ISRO. So there was a heritage. It was going in all ISRO missions. So what we started replacing the RFIC front end portion of that, which is designed by our own designers, and it was fabricated by our own foundry. Now this RF has a tricky thing, because if you are using the same processes which used to go for logic and analog, I think it will not work, because at certain frequencies the losses are too high. So we introduce FSG layer instead of USG layer in the process itself. We have also introduced the thick last metal line. With all this, we have bought it out, this RFIC. In first go itself, it was a successful. We could replace the imported thing at L band. Now the last thing you can able to see is we bought it out SoC, because we are the foundry. So put RF and baseband processor in a single chip, and this is also tested. I think the next stage itself is now ISRO is going to test it. We are doing the packaging. It is a plastic packaging. We are carrying it out. So this is the first time. It is a single chip with both RF and digital baseband processor on the same. So this is a characterization facility. It is a very unique facility in the country. Only ISRO is having. We also have put it here in SCL itself. This is a CMOS image sensor. So all CCDs we can test it at SCL. Electro-optical full setup is there with us, and we are upgrading this facility also. Next slide, please. So this is another thing, high voltage, because we are working on GaN. So this is 3000 voltage also we can test it. So GaN, other things or switches and all, which we are working up till 650 volt and all. So we established this facility so that high voltage devices can also be tested at SCL. Going with the sensor characterization, this is also a very unique facility where each sensor needs its own characterization equipment. So we have full setup to do that. We are doing the pressure sensor regularly, temperature sensor regularly, humidity sensors also. So we have all the chambers lying at SCL. Even gyroscope also, rate table also we have introduced. The next is a very critical thing for cryo type of thing. Next slide, please. So we are testing this also, testing at cryogenic temperature. So that facility also exists at SCL, and we are doing it regularly. For one of the ROIC applications, we are using this facility. Now, quality assurance is also a very, very important thing, which has to be there because any customer wants a qualified product. And when we are dealing with space or aerospace type of things, so we should follow all MIL standards. We are giving a lot of emphasis on our reliability aspects, both the process wise also as a product wise also. So we have a lot of QC checks and all, and our 180 nanometer CMOS foundry is already JDEC qualified. Next slide, please. So these are our facility and equipment. If you want to do environmental testing, mechanical testing, endurance testing, apart from red hot testing, which is a very unique facility we are having, and other tests also we used to do like TID test, HBM test for ESD type of testing also, and radiography facility. Next slide, please. So this is one of the radiation testing facility which we established at SCL. We can do the TID testing, total ionization dose testing. We can go, we have a gamma chamber also. For SEE testing and all, which for strategic sector as well as aerospace sector needs. So this SEE testing, we are taking IUAC help, as well as we are calibrating the VECC setup also. Now these two facilities are there in the country to do this SEE testing. Going with, this is one of the critical area. Nowadays, I think our neighboring countries are sending a lot of drones to us to find it out what are there in the chips. So that is why this forensic of the chip is also a new area which has come up, and that also we have established in the SCL itself. So we can have it, lot of things which is involved to find out what is inside the chip, to remove the package, and the package is from molded compound also. So that also is a very, very tricky process. Apart from that, which technology node was there, that also can be inferred. So all this facility is also there at SCL. Next slide, please. So what are the activities? I will just briefly tell you. I think I already told you about the NAVIC chip. With the NAVIC chip itself, we have put the full ecosystem of front end, where mixer is there, baseband mixer is there at RF at L and S band we used to have. We have a LNA up till S band. Now we have targeted C. We have a PLL also. This PLL is integer PLL. Now we are developing fractional PLL also. Apart from that, VCO is also there, which is working at C band. So this all RF things also, not only we are designing it, we are manufacturing it also, and we are testing it also. Excellent. These are some of the space heritage products which we are regularly delivering. We have delivered more than 20 to 30,000 chips last year to space. Now you can see not only the launch vehicle, but satellites are also using a lot of chips which is manufactured at SCL 180 nanometer. We have also have a lot of international collaborations. The first experimentation which came out from CERN, that is LHC experimentation, where God particle was introduced or discovered itself. 1 lakh chips was given by SCL. We are also part of the next CERN experimentations, where we are expected to give more than 25,000 chips to them. And the last is Trishna detector, which is a very, very tricky detector, which is a 5-band detector. This is an Indo and France collaboration. So their packaging is also very critical. It is a 5-band packaging, so that also we are doing it at SCL. Going with engagements, so we are a part of C2S program. Lot of chips we have fabricated. Last week itself, the fab out of 100 chip was there for academia, which we delivered to IIT Gandhinagar. So this is total 175 chips. Last 14 to 16 months we are fab out this many chips from the SCL. Apart from fabrication, we are also doing the packaging. We are giving the COB packaging. We are also giving the testing support also. Apart from railways, we have other strategic sector like meteorological department and all also. We are also giving lot of emphasis on skill development. Last week itself, we have introduced 1.2 micron PDK in the open source. So anybody can download in open source, where 1.2 micron PDK is available from the SCL website or NILET website, and they can start designing it. We are giving 100 shuttle runs as a free. We are also giving support for packaging, and this will be something like end-to-end mode you can able to understand about the microelectronics from this. So this is other thing where we are doing from classroom to clean room, where we are doing lot of internships are there, faculty development programs is there. From last 1 year, we have put lot of fabs from Parangat to Kalam Training Lab. Other trainings also are going on in that, and we have a tailor-made programs also. Next slide, please. So India is building its chip builders, which I already told. C2S program is there from METI itself. So we have already 175 designs are there. More than 100 designs are already fab out, and already academicians, lot of IITs, NITs, universities are part of that, and they are getting advantage of SCL Foundry itself. So I think these 4 facets of learning, I think, which is very much important. Our Shastra used to tell us, and now we are converting. Next slide, thing. So what you have to do is we have to convert our Vidya to Kala. I think IIT Madras is doing a lot of things in that. I think a lot of policies from the government left-hand side is there, where ANRF schemes are there. A lot of support is there. ISM 2.0 is already announced, which 1.27 lakhs crore in all. So I think whatever we Indians used to have, I think we should start giving it. And we should also, that is why 2 days back when I was in CIA conference, I was telling, we should start sharing it, sharing IPs, sharing our knowledge, sharing our system, sharing our workforce. I think this is something which India can make much ahead of others if we start sharing. Next slide, please. So now I come to the processors. So I think we have a lot of family of processors you can able to see. ISRO is using us a lot, where ISRO has a lot of processor from Vikram to Kalpana, where different architecture is there. Navik V2 is there. OBC is there. Now, with IIT also, there is a Shakti. We have made Shakti C in 1718, then Shakti class E was there in 1920. And now we started implementing in the system also. CDEC also used us, where IIT Bombay is also having a Ajit processor, where 180 nanometer was, process node was used. Next slide, please. So if you can see, this is the Vikram 3201, and the last year Semicon itself, it is known as Made in India chip, first chip which has flown also. It is fully qualified, where it was designed from India, fabricated from India, packaged from India, qualified from India, and it has flown. And this is 32-bit Vikram processor, where all launch vehicles are using it. Now this is another processor, which is a Red Hat processor, which is also coming from ISRO. So ISRO has given us front-end design. After that, the full layout from verification, synthesis, we have carried it out. And this is also a Red Hat design, which has been fab out also. We have tested it also, and now it is going for packaging, and before it goes for a actual use, field use and all. Now going with the another portion, I think, which I already told you, Jay, is one of the things where Shakti is one of our main thing, which I think lot of IIT Madras is helping us out also, where Yamuna 32 is ported on a FPGA now. Already one sensor has been integrated, 4 sensors are due. I am very much hopeful that this month end there will be a flight trial using the Shakti processor on the drone, which will totally replace STM chip, as well as the sensors also we want to replace this. Apart from this flight controller, we are also targeting ESC unit, where this also will be, Shakti will be used for that. So I am very much thankful for IIT Madras to supporting us, where one startup is already engaged with us on this part. Next slide, please. So this is something like, you can see, this is the full architecture. I think it's STM32 is already replaced by Shakti. He has already integrated GPS with this. Now he is targeting the 2 main portion here itself, the pressure sensor, magnetometer, and pressure sensor IMU. I think that also will get through. And the full ecosystem of this flight controller will be from indigenous source itself. So this is something which we are targeting it. And the market here of the drone itself is a huge market in the country. And I think strategic sector wants all the chips from the country itself, and I think this is one of the headway which we are making it. So the next is, this is Iris chip. I think this Iris chip is also with Shakti processor, and this is a flight grade chip, which it is a full made in India type of concept, where this design was done by IIT Madras. I think Shakti team was partner for that. Fabrication was done at SCL Mohali in 180 nanometer. When it was taped out, it was packaged, I think, in Tata Electronics. Apart from that, there were testing was also done by some industry. So a full ecosystem has been developed. I think we should compliment IIT Madras of creating such a ecosystem in the country itself, as nobody else was knowing about it. The next is, I think, C-class and E-class. You are very well aware of. I think we are already using C-class. In next of my slide, you will find it out. In Bharat Shakti SOC, we are using. Shakti E was also there. So there was slight difference on that in packaging thing also. It is for embedded things and all. So Shakti C is mostly we are using it both for drone as well as for Bharat Shakti SOC application. Next slide, please. So this is, I think, industry people are here itself. So this is one of the class of SOC where 19 IPs are there. And I think in 19 IPs, 11 came from IIT Madras itself. So I think big compliment to this team itself. And this, what we have done is, the 3 months itself, the design was completed. 3 months itself, the fabrication was completed. Honorable Minister, we have delivered in November itself, but it takes 3 months for testing itself. And I think the packaging is also taking considerable time. But we have already tested. KGDs were given to industry partner, and we were soon going to replace. So whatever your partner was there, I think one of your sponsor, NXP, we are, I think, replacing him. I don't know, he will sponsor you next time or not. So NXP chip will be replaced. Next slide, please. So this is also one of the things which we are progressing, and the present status is we have already done the testing part itself, and we have also done the COB part of this, but we need the SIP part of that. I think we are still taking help of outside foundry for doing this ATMP operations, but we are very sure in 1 or 2 years itself, because already 3 plants are already there in ATMP. 4th one is inaugurated by Honorable Prime Minister today itself. So we have already 4 plants of ATMP, and further 8 plants are coming. So this, I think, feature also of doing this complex type of packaging will also come in the India in the near future itself. So I think the full ecosystem will get developed, where you don't have to run around after making or fabbing out the chip itself, where it has to be tested or where it has to be packaged. So thank you all for giving me this wonderful opportunities. I will just tell you the way you are working on. So there are decades where nothing happens, and there are weeks when decades happen. So this is the era which we are working on. I think the speed and skill which we should work on, I think we can make wonders itself. So again, thank you for giving me this opportunity to be here, and wishing you a good success in the symposium. Thank you all.
Thank you, sir. That was an insightful presentation about the innovative works that are being undergone at SEL. I now invite our director, Dr. Kamakoti, sir, to kindly felicitate our guest of honor, Dr. Kamaljeet Singh, sir. Thank you, sir. I would now like to invite Shri Gokul V. Subramaniam, sir, President of Intel India and Vice President of Silicon and Platform Engineering at Intel Corporation, to address the gathering about the AI shift and the relevance of CPUs in the AI age.
Okay, thanks. Good morning, everyone. Namaskaram, vanakkam. First of all, my big respect to Professor Kamakoti, dear friend. Thank you for having me here. Sri Kamaljeet Singh ji, wonderful to hear what ACL is doing in India. And of course, Gopal Krishnan, faculty, all the students, all the energy that's there in this room. It's a privilege and honor to be here on a Saturday morning in campus or close to campus and talking to you all. You might wonder what's Intel doing here and what I'm going to talk about. I think it makes sense for me to engage with you, bringing a little bit more about the industry perspective, what we are seeing, and I'll try to weave it into the theme of what the conference you have in the next few days, and of course, the ton of opportunity that's there in front of us as engineers. Reflecting back just a few days ago, I was talking to another student community, and one other thing that really struck me was we are in a time where we can very confidently say that there is no problem statement that technology cannot solve. And this was never the case, and some of us have been engineers for a few years, decades, if not more. We were able to say it before, but I think right now we are at a moment where it truly belongs to us to say that more confidently. Such is the power of what we have in our hands in terms of democratization of technology, but also access to knowledge, being able to learn beyond the bounds of any one campus, school, or one department, and that power is just mind-boggling. So with that, what I want to spend some time is and certainly share my knowledge and open it up a larger perspective of what the shift is happening in the industry. Clearly, if you were to look at data centers, just as an example, only as an example, there was a time data center was all about data, moving data around, and just accessing data. And then November 22nd, 2022 happened. And that clearly shifted a lot of what happens in the data center because of Gen AI. And that era brought in quite a bit of change in terms of, okay, I have now a parallel computing capability. If I can take the single instruction and apply it like crazy with matrix multiplication that was suited for pixel processing, and if I did that, it gave a lot of power to the voluminous amount of data that had to be processed for training. And the entire world and the entire universe, whatever you want to call, gravitated towards GPUs, and rightfully so. That architecture was phenomenally powerful for that kind of application. And then as you start to forward, and you've had a lot of training that has been happening, now slowly but surely, but more certainly, the value and impact of that completely lies on inferencing. You could get into a library and have 1 million books, but you come out with whatever you get out of it and what you can apply. That's pretty much what inferencing is all about. And so inferencing kind of changes a lot about what the compute architecture is needed, what systems are needed. And you get now 2 to 3 quarters, just what's happened in this year and end of last year with agentic AI. That paradigm is shifting even more different based on how physical AI, robotics, reasoning, and acting, and all the things happen. And so many of what used to be a data center filled with only CPUs moved to CPUs being kind of a fly on the wall, 1:8 kind of ratio with the GPUs, to now with inferencing and agentic AI, the whole coexistence of different architectures are translating to more of a 1:4, 1:2, and even 1:1 in some cases. And I say that being very mindful of the fact that what was in last 2-3 years of generative AI that was doing more of chatbots and single-turn interactions, it has really become multi-step. And with multi-step and with agents coming into play, not only are you tokenizing and then being able to run certain agent inferences, you're having to bring that back to do a whole bunch of orchestration. What I mean is, I'm sure pretty much every student and every industry person here, or even faculty here, at some point or the other in the last week, if not last month, have been vibe coding, have been generating code, running that code, trying to test it out, fine-tune it, and then go back. A lot of that orchestration is happening post what the GPU has crunched, which is making CPU architecture a lot more critical and more important. I'm not saying this is a competition versus one processor or the other, and you will see at the end of what I talk that this is a very interesting shift that we have to be mindful of as processor designers, as what we want to do with instruction set architecture. Clearly, AI systems is no longer, give me an answer and I stop. It is fast evolved into a whole bunch of actions, an endless number of actions, all of that being very interactive. And clearly, just going and unpacking what happens when you start to use either VS Code or Gemini or Cursor or any one of these coding agents, you start to look at where GPU is used pretty much for thinking, reasoning, and then start generating the code. And then a lot of the tasks in terms of connecting that with tool chains, with executing it, with orchestrating it, giving it to different pieces, testing it out, bringing it back, retrieval of those, all of that happens in the CPU. So there is kind of sort of the shift, and one has to be very mindful as engineers. Engineering is a field that if you think you've cracked something, that's your downfall, because there's something else in your blind spot that's going to come and shift things. Every time you think that you've solved something, we have a great learning opportunity, and these shifts are pretty important to observe and know what we need to do when we architect the next set of what we want to do. So handling the order of magnitude of instruction and tool calls that are needed now is something here to stay, and that wasn't the case when we were using these processors 5 years ago or a decade ago. Now, there is another aspect also when it comes to closer to physical AI and robotics. Lot of reinforcement learning where the GPU generates a whole bunch of candidate infrastructure, so to speak. Let's not worry about what that candidate is. It could be code, it could be design, whatever. It could be just text, it could be embeddings, whatever that might be. And then you have a cluster of processors sitting there, taking what was generated to really validate what's the usefulness of it or stitch that together to build something. It could be compiling, it could be executing, it could be taking that and putting it into another system and testing it out, getting data back and retuning it, and going back into the reward system, primarily to go back and tell the generating entity, which could be a GPU, please do a better job because I learned all of this based on what you just gave me. And so reinforcement learning is also adding another dimension in terms of how you need to look at a lot of these systems and processor designs. And long story short, our contexts have become pretty big. There's a lot of tokens being used. And you talk about tokenomics, and we in the industry are now burning tokens like crazy to make every engineer super efficient, where they can do really exoskeleton capability. When somebody walks in, including any one, be it an electrical engineer, packaging, RTL engineer, system design, power performance person, who's putting all of this together at the board level, thermal, every one of them is expected to walk with an exoskeleton, which is their capability to do a lot more. And they're using a lot of these tokens. And so there is more agency being built, and when more agency is being built, we're seeing the shift where the explosive token growth, and you can see here in one of these graphs in the second one, it's gone like 100 to 1000x. And a lot of this is going to really, really explode in the coming decade. And that gives a great opportunity for what it means to go build some of these processes and the kind of instruction sets that we want to do. And if I were to summarize the last 5 minutes of whatever I've been talking, one takeaway: CPUs are becoming the center of the shift. It's important. And these CPUs can be in any flavor. It could be an x86, it could be an ARM, it could be a RISC-V instruction set architecture. And they all have their different capabilities that they are bringing. It could be an AMX for matrix multiplication, or it could be what ARM brings with its scalable extension engine, or what RISC-V has with the vector-based dot product stuff that you can do as a modular capability. But all of them are trying to play with 1D, 2D vectors in different forms and ways. If you were to look at it, one might be trying to solve it at an industrial kitchen level. Another might be trying to do it at your home modular kitchen level. And another thing might be trying to do it like, here's my cool onion chopping machine level. It doesn't matter. But they all have a space for you to play. And each one is bringing in their own context phenomenal capabilities and accelerators that are important for us to go solve problems. And with inferencing and doing more at the edge and agentic stuff, the ability to do some of these accelerators in the CPU, be it RISC-V, ARM, or x86, they're all trying to operate in different thermal envelopes, different power envelopes. You know, AMX might be more on the service side, but then even on the Intel side, you have the AVX10, the VNNI that's being done on the GPU, or even shave architectures on the NPU. All of this we're trying to do in like 5, 10 watt, 15 watt, 20 watt. You might also want to do it at a microcontroller level. That's still critical. So the fact that this shift is really going to give more ability for ISAs and processors to do some of their own internal capabilities in their design or develop their indigenous accelerators is now a huge minefield of opportunities. And the places where these are getting deployed is not limiting any one of them. And you have a part to play in all of these. And coming to the second part, which is kind of the theme of this conference, around security. Now, and I just want to spend a few minutes just give you an idea of where the industry is and what the industry is looking at. Securing AI is way beyond the usual software sandbox. You know, the WAF, the Web Application Firewall, was good up to a point, but we're seeing the reality with a lot of autonomous execution. The security threats are the several layers. It's like on the top of the application, on the side from the network, from underneath, from within the silicon, from within the SoC. All of these are become extremely vulnerable entities that are critical to make them rock solid or really secure and hack-proof. And wanted to give you a view that of the three big parts in the security, there's the application layer. As you run more and more agents, and even though there might be human in the loop, there are several agents that can go autonomous and become rogue, and we've seen examples of those that happen this past month, this past week, where things have gone out of context. Maybe it exposed a bunch of GitHub code, or it ended up doing something that we intended not to do. And like Professor Kamakodi said, we want to design chips on what it should do, but we should also worry about what shouldn't do. And these are very critical aspects. Second thing, there's like crazy amount of network-driven metadata intelligence that can be picked up, even though every bit is encrypted, that there are signatures and footprint that we leave that are very easy for somebody to go and hack. That's the network layer. And the third one is, as we get into the silicon, because of the various complexity in the microarchitecture and all kinds of power gating things that we do, that gives another opportunity for security holes. And so it goes far beyond saying that if a firewall is broken, my security is breached. The attempts of exploitation is far more sophisticated than any firewall that used to do in the past. And just to give you an example, with a lot of agentic workloads and agentic workflows and AI, and there is an open source security forum which looks at every year what are the top 10 security areas. And this is an example of what are the top 5. The goal can be hijacked on what the agent wants to do. You can compromise on the supply chain. Obviously, the other big one is your identity as you start to build these, be it your name, your password, but even your financial data. Tools can be misused because a lot of these agents are actually saying, go compile, go get it from here, go put it in another tool chain. It could be even using EDA, IPs, and things like that that could get abused. And these can have a cascading list of failures just at the application level. At the network level, this is very interesting. There was a study done, and there's a real research, where even though you encrypt, and as you start sending these packets, and if you're, let's say, an AI system, and you're in a chat session, let's say with just ChatGPT or whatever your favorite AI framework is, there's a lot of one-to-one conversation going on. Even though every one of this conversation is encrypted, the frequency at which you're sending these packets, the size of these packets are good enough for somebody in the network to snoop and figure out what needs to happen. And they found out that these are really classification that can have very high accuracy. Think of an envelope that you've sealed and you're sending back and forth. You could have encrypted and sealed it really well, but the weight of that envelope, which is the size of the packet, and how often you're exchanging is good enough for somebody to go play with from a network security. The third one's probably closer to this group, and maybe you will nerd on this a little bit more than the other two, is, with Dennard's law, and Dennard's law is already, I don't know, some of you probably weren't born when it already saturated in 2005, but the fact that you can pack more transistors and not have the same benefit of running it at low power has become a big problem, and because as you pack more and more of them, there's leakage, and hence you got to figure out what you want to do as you increase your power, and then you start applying power gating schemes in your silicon design, your chip design, which means when I'm not using it, put my IP into the lowest power state. When I'm using it, bring it back from reset, things of that sort. You could easily have a very unassuming thread sitting there in the SoC, not looking vulnerable at all, and just doing a bunch of things with the silicon as test packets to see how quick or how slow it's reacting. And that signature tells how your silicon architecture is. What did you really power gate in that section of your SoC and what you did not? And that becomes, and this is a Whisper leak a study that was done. There are a couple of them on the network Whisper leak and at the silicon level, which are also proving to be vulnerabilities that we need to be careful about. And with a lot of the MOEs and mixture of experts that we are applying, these are very critical to address at the silicon level, at the chip design level. So with those three, right, application level, network level, and the silicon level, what the next generation threat metrics look like is you have an attacker, they can manipulate the agent's logic, they can decode the traffic pattern even without even looking at what's inside it. They can extract the model routing that you're doing. When you run an MOE inside the silicon, how you awake certain accelerator or not. All of it they can do without breaking the sweat or breaking anything on the traditional software sandbox. So it's scary, but it's also very exciting if you're an engineer, because there is a lot of work, a lot of IP that can be generated here, which is very important for things that are going to impact people's lives. It doesn't matter, right? And it starts with security at the hardware, at the silicon level. And so just putting it all together, some of the key shifts that's happening is there is growing investment in inferencing. I think it's a no-brainer. Everybody understands that we got to eke out the value of AI, and the only way you're going to do it is by doing a lot more inferencing, a lot more at the edge, which means a lot more processor needs in the edge for that. The workload profiles, the fundamentals of the workload profiles that we use to build our chip has changed drastically. There is a decade's worth of knowledge that we've built as an industry, as a learner of processor design, but the workloads that we used are shifting big time with agentic AI. Orchestration of all these workloads are happening on CPU. And that's a huge opportunity for anyone developing processors. Inferencing, disaggregating what's happening. Where do you do the actual prefill? Where do you do actually the decode? And then where you do all of the orchestration. These are all getting disaggregated. When you aggregate this, then there's some that's happening in the GPU, because when you're prefilling, you're doing a lot of parallel operations that you want to do to generate the text, fill in the KV cache. And then when you want to decode, that becomes extremely memory-bound operation, because you need to get all of this KV cache to generate the next set of text and figure out what you want to do. And then as you orchestrate, you want to run all of these tool chains, you want to execute tests. So you have different set of challenges with the processors and CPUs. So disaggregation is becoming the nature of the beast. And obviously, last but not the least, the security is clearly a must at all levels: network application level, network level, and security. So as you look ahead, I want to leave you all with the thought that it's a time where it's really a fun, interesting space for anyone who's working on compute. And it's heterogeneous. So don't be worried if you're working on a microcontroller, if you're working on ARM or RISC or on x86 or anything that might be new. Heterogeneous compute is the name of the game, and that needs, it's going to be how the industry and everything is going to evolve, which also means there's a huge part in how the instruction set architectures are evolving. Domain-specific accelerators will continue to happen. There could be GPUs and NPUs, TPUs, and all of those. And end-to-end security is going to be fundamental to how we design these processors and get them out there for the next decade and next few decades of how everything is shifting in our world with AI. With that, I just wanted to wish you all a fantastic next couple of days. It's amazing to be in this room and be in this campus with so much work that's happening around what we want to solve for the world in the next decade, and truly confident that lots of first is going to come out of IIT Madras. Thank you.
Thank you, sir, for that eye-opening session. I now request Professor Gopalakrishnan, sir, to felicitate him with a token of appreciation.
Thank you. We regret to inform you that Sri Manoj Jain, Chairman and Managing Director of Bharat Electronics Limited, is not able to join us for the symposium today. We extend our sincere thanks to all our dignitaries for their insights.
We now request the dignitaries to kindly take their designated seats amongst the audience. Quick reminder for the audience, kindly refer to the website for the agenda. If you have any queries, please feel free to reach out to our volunteers with the volunteer tag.
Next on the agenda is an address from RISC-V International. To share an overview, we would like to invite Lavanya ma'am, founder and CEO of Vyoma Systems, on stage. She is an official RISC-V International ambassador. With over 15 years of experience in processor verification, she has worked with leading semiconductor organizations including IBM, ARM, and Rambus, contributing to IBM Z, ARM Cortex-M, and RISC-V processor development. She currently leads process verification initiatives at the Shakti Group, IIT Madras, and she is also actively involved in advancing in India's open source semiconductor ecosystem. She holds an MS degree in computer science and engineering from our IIT Madras. We welcome Lavanya ma'am on stage, please. Thank you.
Hi everyone. A very warm welcome to this third Digital India RISC-V Symposium. It is wonderful to see all the students, researchers, startups, and industry coming together for this event. It's an event that is also special to me personally because all the roles that was mentioned in the bio converges in this one single event. Most importantly, as a RISC-V ambassador, but as a lifelong student of Professor V. Kamakoti, who not only architects the Shakti processor system, but also architects students' careers by sitting as one in the audience to being able to handle this stage today. As a RISC-V ambassador, I have also had the opportunity to engage with the RISC-V ecosystem over the past year, and we want to present what happens in RISC-V at the global stage, as well as in India, and more closely at Shakti Group at IIT Madras. RISC-V is no longer an open ISA that is trying to prove itself. It has already arrived. Today, it's about building products, software, and secure systems and AI accelerators, which is the theme of the symposium. And it also contributes to high performance and computing platforms. We will see a lot of conversations on the architectures, the processors, as well as the products that is coming out of this ecosystem in the talks as well as in the stall area. At the same time, we are also seeing world's largest technology companies building their own silicon. This makes processor architecture, design, verification, software, and open standards more important than ever. So RISC-V is becoming a conversation topic at the global stage. This year, from the India's perspective, we also had the opportunity to take the RISC-V contributions and present it in the Open Source Summit at Mumbai in June. So together with RISC-V International, we showcased Shakti's indigenous processors as well as the startups that is coming out of the Indian community. The response was overwhelming. Software developers, Linux kernel distributors, students, and startup founders were excited to see the real Indian taped out silicon. And as is always the case, we understood that all the stakeholders of this ecosystem come together to drive this next generation of RISC-V success. It reinforced a simple message that such strong ecosystems are built when both the communities have conversations like what we are going to have today and drive it forward. And this journey began at IIT Madras. The vision, spearheaded by our director, Padma Shri Professor V. Kamakoti, through the Shakti Processor Program, has grown from the academic research in the computer science department to a thriving ecosystem of startups, industry, and indigenous semiconductor ecosystem. Today, the exciting work is underway at the Shakti Lab for increased adoption of embedded and AI accelerator processors, but also having several crucial tape-outs in the coming year on advanced technology nodes. We are seeing and proving that research steadily translates to products and then becomes the real-world impact. That is also the vision behind DIR-V, to bring together all the stakeholders for the past week and in these 2 days to have the conversations on building the vision for a semiconductor nation. Before we begin the technical sessions and startup showcases, it is my pleasure to introduce someone who has been a strong supporter of this Indian RISC-V ecosystem. Although he could not join us in person this year, he has graciously shared a recorded message for the DIR-V community. Please join me in welcoming Andrea Gallo, CEO of RISC-V International. Before joining RISC-V as VP of Technology, Gallo worked in leadership roles at Lenovo for over a decade as Vice President of Business Development, driving the company's membership acquisition strategy and previously managing the Lenovo data center and cloud. Before Lenovo, Gallo was a fellow at STM Microelectronics, where he led the optimization of hardware-software architectures for new smartphone and telecommunication ICs. Let's all hear it from him. Kindly play the video for the message.
Hello, I'm Andrea Gallo, CEO at RISC-V International. Thank you for inviting me to the third DIR-V conference. As a member of the RISC-V ecosystem, you are all part of a global organization. Our membership is uniformly distributed across the globe, across all the geographies, and we all collaborate to grow and curate the RISC-V instruction set architecture. I like to remind that a standard is a catalyst for innovation, and just like USB or the Wi-Fi or the Internet protocols, RISC-V is an open industry standard that you can download freely from the website wherever you are in the world, be it in California, in Silicon Valley, in Texas, in Europe, in India, or elsewhere in the Asia Pacific. And locally, you can design your products compatible and compliant to the RISC-V specifications. This was further endorsed by the ISO IEC, the Joint Technical Committee 1, last September, when we were recognized as a publicly available specification submitter, a PAS submitter. So ISO and IEC, they evaluated, analyzed the way of working at RISC-V, how we track consensus from all the members, how we develop the specifications in a transparent way, and they awarded us the status of platform specification submitters, which means that in the future we will submit the RISC-V specifications for evaluation and hopefully for ratification as an ISO standard. We organize our events everywhere in the world, from the RISC-V summits to bringing RISC-V to industry events like Embedded World or the AI Infrastructure Summit. We organized a RISC-V Automotive Conference last September, and we organized all together with the local communities the RISC-V World Days, including India, last year. So thank you for being part of these worldwide initiatives. Startups and academia engage with RISC-V because it's so easy for them to start working on the RISC-V specifications without any legal framework, accessing the specifications under the Creative Commons license, and also leveraging available designs, IPs, blogs available from other academia, and immediately add your competitive advantage and added value. Multinational companies and countries invest in RISC-V because they have the confidence, thanks to the RISC-V model, they have the confidence that they can define and control their roadmap, their destiny, their digital sovereignty strategy. Thanks to RISC-V, wherever you are in the world, you can invest locally and engage globally in this RISC-V worldwide ecosystem. RISC-V is seeing a continuous, tremendous growth, and in 10 years, from 2021 to 2031, we see a growth from 2.5 to 33.7% across all the market areas, from IoT to computing to automotive to networking, everywhere. And the investors believe in RISC-V. Just in the last few months, Sci-5, Accelerate AI, OpenChip, they all received a massive amount of investments from venture capitals. And Edge AI and cloud are the areas of fastest growth for RISC-V. So AI at the edge and cloud and AI in the data center, of course. So how are we going to address these opportunities and make them become real business? We recently ratified the server platform specification. In a data center, compared to more fully controlled embedded products, in the data center there are additional requirements to comply with industry standards, requirements to provide quality of service, reliability, availability, serviceability, security, but also performance, and so on. And so the server platform addresses all these needs. It adopts industry standards like UEFI ACPI for the bootloader and the runtime services. And this is possible also because the UEFI forum in the ACPI 6.6 added specific support for RISC-V in the ACPI table. So it's a joint effort. And the server platform also standardizes common peripherals that are close to the RISC-V core and that they don't provide any competitive advantage. Actually, they are an unnecessary differentiation. And in a data center, the operating system distribution vendors, they want to see server platforms that all behave in a similar way when it comes to bootload architecture. And so the server platform specification builds on top of the RVA23 profile specification regarding the RISC-V extensions, and it builds on industry standard boot architecture. So it provides compatibility at the operating system and especially the Linux distribution level. So RVA23 is the profile specifications that we ratified 1.5 years ago. And now we see that 2026 is the year of the RISC-V application processor silicon. There are so many processors and designs that are becoming available as we speak. Sci5, TensorRent, Epic Semi, Akiana, Next Silicon, MIPS, BOSC, Schwanti and Dam Academy, Space Meet, Nuclei, they are all providing their designs, IPs, and real silicon that comply with the RVA23 specification and that are high-performance application processor designs and products available in real silicon. So this is really the evidence that 2026 is the year of the high-performance RISC-V application processor. And I'm excited to see that Deep Computing, the first ones to design RISC-V-based laptops for the RISC-V developers community, they recently upgraded the motherboard for the framework laptop to support the first RVA23 chip from SpaceMeet, the K3. And this is fully compatible with the framework laptop 13 specifications. And it is the first one that brings high-performance RISC-V application processors in a laptop that you can use for real work. Hardware, of course, and specifications are not enough. We also need to foster and grow and mature the software ecosystem. So on one side, companies like Ubuntu have endorsed the RVA23 profile specification since the very beginning. And their Ubuntu LTS fully supports RVA23 for long-term support. And in addition, we work closely with the software ecosystem, with our partners. We are providing Yocto fully supported officially for RISC-V. Since November 2025, RISC-V is one of the 3 officially supported instruction set architectures. But we're also working closely with the Zephyr project and with the Edge AI Foundation and with Edge Impulse on the Edge side and the operating system distributions, of course, for the data center, and with RISE, the RISC-V software ecosystem. You know that they are focused on coordinating the work on open source software for RISC-V, accelerated through specific funding of specific work and making it available upstream. Together with RISE, we set up native GitHub runners, CI runners for RISC-V. The numbers are growing every day, more than 13,000 workflows, more than 260 repositories, hundreds of organizations. This is all available through a build farm with more boards being added as we speak. And the work has been focusing on improving support for Python, Go, OpenJDK, GCC, LLVM, PyTorch, Llama CPP, IRI. So overall, in these very short few minutes, I covered some updates on the evolution of the specifications, on availability of real RISC-V application processors in 2026, and the evolution of the availability on the software. RISC-V as an ecosystem is continuously growing very fast. We used to say that RISC-V is inevitable. We used to say that it's not if, but when. Actually, this year, this is when we can say that RISC-V is now. I wish you a great conference at the Digital India RISC-V event, and I'm looking forward to being with you at one of the next events in the future. Thank you.
We thank Andrea for his message, and thank you all for joining this community for the next 2 days. Thank you.
Thank you, ma'am, for that enlightening address. This concludes the inaugural segment of our morning sessions.
Before we break, let's look ahead at what is in store for the afternoon. We have an exciting lineup that you certainly do not want to miss. We will be diving deep into the security challenges of the RISC-V ecosystem with an expert panel, followed by exclusive keynotes from industry giants Mindgrove Technologies and L&T Semiconductor Technologies. To cap it off, we will begin the first set of presentations from the Grand Challenge participants. It is going to be an action-packed afternoon. To ensure everything runs smoothly for all our guests, please note a few quick announcements. For questions or assistance, please approach our volunteers wearing the official ID tags. Also, the full agenda is available on the website. Please keep checking it for any live updates.
As we have a large gathering today, we are managing the flow of movement to prevent overcrowding. We have organized lunch into 2 distinct slots for the participants, which you can find on your ID card marked as delegates. If you are in slot 1, the timing is 12:30 p.m. to 1:30 p.m. If you are in slot 2, the dining timing is 1:30 p.m. to 2:30 p.m. Now, I would request you to directly go into the designated exhibition halls to engage with our partners, and then to the dining area. We kindly request everyone to strictly follow their assigned timings. We request your cooperation and avoid overcrowding to ensure clear passage for all the attendees. We look forward to seeing everyone back in this hall by 2:30 p.m. sharp for the afternoon sessions. Thank you. If you have any doubts or queries, you can always reach out to the volunteers with the volunteer tags. They will guide you the pathway. Thank you. Participants, you can also use those doors in the back for the exit.
Hello, hello. Sound check, sound check. Mic test 1, 2, 3, check sound.
I request all the people inside the auditorium to kindly settle down and take their seats. We will be beginning the afternoon session shortly. Welcome back, everyone. We hope you all had a refreshing break. The afternoon ahead is packed with exciting events. We kick off the crucial discussion on silicon security, followed by keynotes from industry giants and the much-awaited Grand Challenge presentations.
As India's semiconductor ambition scale, securing the silicon foundation is more imperative than ever. Our first panel discussion focuses exactly on this: security in the age of RISC-V, understanding the challenges, opportunities, and the road ahead. To moderate this insightful session, we are honored to have Professor Chester. His research interests are hardware security, applied cryptography, side channel analysis, and operating system security. He has over 100 publications and also it's the Center for Cyber Security Trust and Reliability at IIT Madras. We kindly welcome Professor Chester onto the stage and initiate the discussion.
To share their expertise on the topic, we are privileged to host a distinguished panel. I request the following experts to join us on the stage. We have Shashwat T.R., co-founder and CEO of Mindgrove Technologies. Mr. Arjun Menon, co-founder and chief engineer of Encore Semiconductors. Next, we have Mr. Saurav Roy from NXP Semiconductors. Next, we have Suganya ma'am from Society of Electronic Transactions and Security. We now request Professor Chester to take the stage and initiate the discussion.
Yeah, so thank you. Yeah, we all know where Linux started with, right? So it's a well-established open source thing, which essentially started maybe the early 90s or late 80s or so. And what we see today is that Linux is first of all made open source. And what we see today, right, over a span of a couple of decades, is that Linux is now adopted in large number of systems, right? It's the most widely used operating system in the supercomputers. And also on the other extreme, it's highly popular in embedded systems also, right? So today, as we sit here, RISC-V is essentially taking its place, right? For what Linux, the open source operating system, did for the OS, RISC-V is trying to do the similar thing in hardware, right? And so RISC-V, of course, is the ISA, the open source ISA, and very, very importantly, it's trying to essentially democratize and open up the hardware ecosystem, right? Especially for processor design. Now, side by side, with the increased amount of cyber threats that is actually there in today's world, with the increased amount of connectivity, with IoT and all other wearable products, and the threat of cyber attacks is essentially increasing. So given this very interesting times, right, so we want to essentially discuss about what RISC-V can essentially do for security, right? So as the name of the panel is Security in the Age of RISC-V, Understanding the Challenges, Opportunities, and the Road Ahead. So with me, I've got 4 eminent panelists. Shashwat, the co-founder of Mindgrove, has over 15 years of experience working across the stack, from systems engineering, signal processing, and machine learning. And more importantly, as many of you know, so Shashwat was also the lead architect of the secure IoT chip, which is essentially developed by Mindgrove. Arjun has completed his MS from IIT Madras, and I remember very well his MS thesis on one of the first security extensions for RISC-V. And since then, he has co-founded InCore, where they do consider security as extremely important, and in fact are also developing a secure RISC-V core. Saurav Roy is a fellow at NXP. He comes with an incredible extensive experience in CPU, DSP, NPU, and SoC architectures. We've spoke, I think, multiple times over the past, and has a lot of insights about how secure chips should be essentially designed ground up, right? And Suganya is someone, again, I also work very closely with, and has over 20 years of experience, but from a different perspective, right? Suganya looks at the certification and evaluation of chips and embedded devices with respect to security. Right, so we have an excellent panel, and we're looking forward to this great discussion over the next hour, right, on how the interplay between RISC-V and security. Right, to start off with, maybe we'll just go around and just provide your introductory thoughts on RISC-V and its implications for security.
Hello. Hi. I think the very first thing that comes to my mind when I think about RISC-V and security is that everybody knows that RISC-V is an open standard, right? RISC-V tells you these sets of instructions that a particular processor should execute. Now, people say that the most secure anything that you design that has to be really secure also has to be open, right? That is the very first thing, because if somebody gives you a black box, you don't know what is inside it, and hence you cannot trust it 100%. You just have to believe what somebody says, right? That said, openness is just a necessary condition for security, but not a sufficient condition. In today's world, when AI is booming so much, and you see that there are so many devices that are going to be coming, that you will be interacting with on a daily basis. You will be sharing every single data with multiple devices, right? All of these devices have to be secured. The attacker just needs one device or the weakest link in this chain for him to break into and get into this entire network of devices, all of which are connected. RISC-V provides a platform where people can go ahead and now really innovate and do whatever they want to do, right? If you have a closed system like an ARM or an x86, there are only people inside the company that can innovate, and you have to just believe them on what they're providing, versus RISC-V, because it is open and you also have a lot of open source implementations, people can go ahead and implement whatever the security measures that they want depending on their threat model and actually verify if everything works correctly. Even if you look at the way this landscape is evolving, there are two primary, one of the most famous, open source efforts that are really being adopted by the industry. There's something called OpenTitan and there's something called Calyptra. OpenTitan is more adopted in the embedded domain where you want a root of trust, you want secure boot and so on. Calyptra is meant more for the server class domain, right? But you see that there are both of these efforts which are really being adopted by the entire industry. People are standardizing on this, right? Tomorrow there will be a time where you have to be Calyptra compliant to be able to sell chips in the server market, right? So yes, I think RISC-V has opened up this possibility that people can really innovate. They are no longer restricted in terms of what they can do. Now the effort is just to go ahead and implement and make sure that everything that is implemented is indeed correct, right? To actually verify that whatever specifications that you have thought about, whatever attack model that you have specified is complete, and all the solutions that you've provided that you're implementing indeed does protect against the threat model. That would be the next effort.
Sorry. So the reason I asked Arjun to go first is I thought it makes sense to go from ISA level and then to systems. So on the ISA level, there's a lot that has already been done and a lot that has gone into how we envision security in a RISC-V code. But from a system level, I think, I think system architecture is still evolving, whether you're talking about RISC-V or ARM, and or anything else for that matter. And some of the more exotic architectures that we build as accelerators for different kinds of machine learning and so on. I think isolation of separation of concerns, building to a particular spec, building to a particular requirement, and all of these things are always complex. And to me, what RISC-V offers is a way to, in the security space, what RISC-V is offering us is a way to have a common language which is open. And so you can actually adapt the implementation while keeping the language common, while keeping the interfaces common. And you can increase or decrease the security requirements depending on the threat model and the mission that the device is going to go into. So to me, the first thing that comes to mind when I say RISC-V and security is the fact that I can build whatever security model I want on the system and still keep a common platform above it for the developer to interact with. Sir,
Am I okay? Yeah, so I come from a different perspective. So I actually lead the RISC-V development in NXP. The biggest customers for us across all business units are the secure elements and the security cores. And one of the things that we do is we do a lot of custom extensions in security. We cannot teach the other processor vendors the secret sauce of security that we put in. So the maximum number of products that we do for different chips have been, like, over the last 5 years, have all been RISC-V. We don't always publicize it, but you will be appalled to know most of the modern day SDV chips, whether the topmost IoT chips, even the secure elements we are doing, the secure core is always RISC-V. Because that's where we can do a lot of custom extensions. Like I can give like say for example, control flow integrity, right? So in CFI, there are standard extensions, but those standard extensions don't always still satisfy the customer needs. So we add a lot of custom stuff over that. Similarly, in post-quantum crypto, which is now coming up, we have post-quantum crypto accelerators coming up in our new security elements. So I think security is one of the major drivers why RISC-V actually flourished, at least in some of these companies, right, who were doing, like most of our cores are from other vendors, but because we cannot teach security to every other guy, and which is our selling point, we actually moved to RISC-V and do a lot of custom extensions with that. Of course, when everybody else knows, it's not very long, people will not know about it in 2-3 years, then we standardize it. But that initial few years, you get a lot of benefit by doing RISC-V course, which gives you these custom security extensions.
Very good afternoon, everyone. So I am coming from a different background of the evaluation lab, right? So when I see the RISC-V, as Arjun likely said, it is available online. OpenTitan and Calyptra is there. So there is a challenge worldwide, and we are able to do the vulnerability analysis of the source codes. So if we are able to do in that stage, then definitely we can, because one evaluation lab cannot evaluate all the vulnerabilities or even anomalies may be there. So it is always good to have an open source so that it can be completely evaluated and validated. And if it goes to the hardware, then the vulnerability in the hardware may not be exist or may be minimalized at least for its lifetime, 15 to 20 years. So I always prefer to be the open source or the source code is available open for the evaluation. So security cannot be achieved by obscurity.
Thanks. I think that was a lovely opening point and also very interesting. I think it's also sets a very interesting thing because we have two different versions. So Saurav, I think you had a different version about customization, right? And possibly, as you mentioned, that's what the edge RISC-V has, right? And Arjun, I think Shashwat in particular mentioned that we need to do a lot of customization, but keep the systems view similar. So like to kind of discuss that. So customization may also create fragmentation, right? It may make compilation or software stack become less portable. So what is your take on that, Saurav?
Yes, I think that's definitely a big problem, and that's why I added that after a few years, we would like to standardize it, because we don't want to carry that software overhead for decades and all this, right? It's a big cost. But the initial few years is where we make a lot of money, and there the customization helps for guys like us whose security is the strength, right? For companies where security is the strength, RISC-V comes in. But you're absolutely correct. When we basically get to the point we see others also doing the same thing, we standardize it. I mean, there's no point in carrying out those custom extensions. But custom extensions are very important because for any organization to make a differentiation in the product, you don't want to be a Me Too product. So there are too many Me Too RISC-V cores in the market. I can't go and sell that even internally to my business lines. So that customization gives that edge for the first few years. So, and the other costs at that time doesn't matter. Because if you have a great PQC accelerator, nobody is going to question your software investment and all these. Because you will sell that and you will sell that in huge numbers. But if some other guy comes up with a very similar PQC accelerator and open sources it, we also join the standard body and try to make it like similar, and then we standardize it.
So Arjun, Shashwat, so specifically like just highlighting Saurav's point that especially at the startup space, right, there are multiple different RISC-V initiatives, RISC-V startups, and where do you see the edge if you're...
So I think there is a little bit of a big company versus startup thing going on over here, because for us as a startup with not many people, we cannot maintain that software. We cannot maintain that compiler stack, because that is an overhead that goes over our heads. So for us, the availability of standardized tool chains and standardized platforms above is something that makes it competitive. And for you, while it helps, I think you can take that overhead and go a little further. You can push the boundaries a little bit. So there is definitely that tension. But I think even the fact that we have an 80-85% common platform is already getting us to a point where we don't have to guess again, and we don't have to go sit and recertify 85% of the platform for every single change that we make, and that in itself is valuable. So I think there is enough of a commonality in this, in what we are talking about, that you can figure out and let every company or every team come up with their own versions of how this works. Fragmentation is a problem, I know, but let's just take a look at Linux itself in the question of fragmentation, because I remember in the late 90s and early 2000s when people were saying, oh, Linux is fragmented. Yes, it is. But then we came up with things like systemd. We came up with things, we came up with innumerable methods on the top, on the application stack, such that today, for a very large percentage of the things that we do, we don't even have to do anything but change the compilation flags from MARC is x86 to MARC is RISC-V or MARC is ARM, and the whole thing just works. So yeah, I mean, there will be custom extensions. You will have to make sure that GCC or Clang support it and so on. But that, I think, is not the bigger problem that we are trying to solve over here.
So I think as a startup, our aim is to actually try to make as much money as possible with us by putting in as much little effort as possible, because we cannot put as much effort as NXP can put, right? That said, I think 80% of most of the security features don't really require customizations. These are mostly standard stuff, like what Shashwat was also mentioning, which is true, and that is what we will put most of our initial efforts on building all the very basic building blocks that will be required for almost all applications. At the next level, you would still do customizations, but something that will have very limited overhead in terms of software. For example, I can probably go build an accelerator which completely does a particular encryption or hashing or whatever and just returns the result. The abstraction at the software level will just be a function, or maybe 4 or 5 functions, which I can still just hand code it in assembly or have some hard coding done there. And then you just reuse these 5 functions across your complete software stack, right? So as a startup, our effort will be in coming up with all of these rest 10%. So if you think that 80% is the common case, 10% is something where you can still get away by doing some tricks, right? You can have very small software programs that can be reused at a higher level. The rest 10%, yes, that is, fragmentation is definitely a problem. And like he said, I think with time, when more people start adopting and start using certain features, that just becomes the standard. That becomes the norm, and then eventually it will become standardized.
Maybe this question is for Suganya, right? So, so typically when you evaluate hardware, right? So it's mostly black box, right? So you'd have maybe an ARM or an Intel chip inside, and then you analyze for, say, side channels and so on. Do you think your evaluation would essentially change because now you do have RISC-V and you do have, you may have more visibility inside the chip?
Yeah, sure. Because if I know the architecture as an evaluator, then the evaluation process will be very transparent. So I can evaluate each and every point of interest. If it if it is the side channel leakages, and if it is a cross execution or anything, if I know the source code and the hardware which is fabricated from that source code, I'm having golden sample. So the evaluation process will be really easy. But if it is a black box, then I have to guess. And yeah.
So basically, if I understand it, the open source aspect would actually give you more trust in the hardware?
I strongly believe in that, yes.
Okay, so that actually leads to a different question, right? So to be truly open source or something equivalent to Linux, one would need to also open the source code for RISC-V. And I do know companies, at least RISC-V startups, which claim they are like completely auditable because they've open sourced their source code. So what is your take on like open sourcing?
Yeah, I'll take it.
So I think, for example, if you have to certify something, yes, you will probably have to open up your code base to the certifying agency, not necessarily everyone. That said, there already exist, for example, Calibra and OpenTitan's success is primarily because they are open source and they are auditable, and more importantly, they are backed by all of these big companies that are actually auditing and correcting things. So there already does exist some solutions, but I think those systems are still, for example, Calibra, you can use it in systems where you don't want to customize anything, you just want to take it, drop it, and that Calibra itself has the core inside it, right, which can be used only for security. You cannot use it for anything else, right? So maybe some systems that works, but for some other systems, you may want to reuse the processor for your actual application. It is just a single processor that does both. It takes care of things like secure boot and probably also runs your actual application, right? And that can have n number of other optimizations that are required for the application layer. Now, those things, of course, as a startup, because that is our IP and that is what gets us money, we cannot always just open source the entire thing, right? Startups may still choose to open source certain parts of it, parts that really form the trusted computing base and is not so critical, an IP. Certain parts can be made open source for the entire community, but the entire system as such, that will probably be opened up only to certain certifying agencies that will certify and guarantee that there are no bugs today, and that is basically how the industry works today anyway.
I just want to riff on what you said about OpenTitan, right? OpenTitan itself is open, and that gives you a golden reference to work with. And if you have an evaluation done on something like that, which is already open source, and if the system under test rhymes enough with an open source implementation, you can take a large number of those tests and port them over. That's where that base layer being common really helps with things like certification also. So under that, the place where you still have to end up guessing is things like the actual implementation of the side channel protections, for example, and see whether they. But no, very often those are not even at the RTL levels. Now, very often those things might come straight down to the physical level, and you might have. So there is like, at what level are you going to stop over there? So I think the fact that a large portion of the system is open, even if you're not able to open up the RTL or not able to open up the PD for whatever reason, commercial reasons, or sometimes we are bound by NDA to not be able to open up what we have. Sometimes we're bound by other requirements that we cannot open up the entire RTL. But even then, I think the fact that we are building on a lot of open collateral will itself make the job of not just certifying is one concern, but the real world performance on something that has been validated is definitely a place where you can expect an easier route.
Yeah, I just wanted to add, I completely agree with Shashwat. I think, for example, the Zuentai processor, that's open source, right? And after they taped out, when they were running software, they basically figured out that there is a vulnerability in it. There was a speculative attack that was possible, and the solution was to just disable the entire vector extension, which basically brought down the performance by like 70%, right? So I think being open source is just one criteria, but that is not the only thing for security. You really have to come up with better methodologies of verification and writing properties, probably tend more towards formal in order to verify that no bugs or vulnerabilities exist.
Yeah, I think I would agree with both of them. And especially for us, it's really is counterproductive to open source our design, right? So, in fact, what happens in many of the secure cores is the RTL is even not visible to the SOC teams. So, because those do have lot of you have sandboxes in there, you have lot of signatures in there. So it is also you have to work in restricted environment even in our IT. If you are working on some secure elements chip, so that only a handful of people get access to it even within the company. So from that perspective, I think it depends on what type of security we are talking here. But if we are actually doing a very secure type of a chip, it's actually very different. We don't want to open source things, but for certification, yes. I mean, there can be scenarios where under NDA we work with a certifying body and open source some part of it. But it's a very, I would say, not very prevalent. The more thing at least in the big organizations, is to limit the number of people who know all the security stuff inside the chip.
I'd just like to add one point over here. There's probably also a difference that you have to differentiation you have to make over here between an open architecture and an open implementation. And you can have a closed implementation and an open architecture, which is again still very valuable.
So I think it's interesting, right? Because what we're actually seeing coming up here is, and not possible with other standard chips like ARM and things like that, is that RISC-V at least permits to certain extent, right, under NDAs as you mentioned, that you could have visibility to either the architecture or at the code base as well, right? So Sugani, I just wanted one feedback from you, right? So a lot of the certification, it's mostly a checklist kind of thing, right, today. But with a much enhanced visibility and a lot more that we can actually get, do you think we need to come up with new security standards or new security certification policies? Right? Just to give you one hint, one thought, right? Arjun mentioned about the speculative execution bug. Today, I don't think any certification actually covers that because you can't. Given a black box processor, it's almost impossible to identify speculative bugs. But on the other hand, with partial or completely open sourced implementations or under NDA, such bugs could possibly be identified. So does this mean that certification needs to be ramped up and you could possibly have like ultra secure chips, right, which meets not just your FIPS standards and ISO standards, but even much more than that?
Yeah, so if we see the security certification, so when we see ISO 19790, so there is a crypto boundary inside it. So every interfaces, so every bus or any interfaces that access the memory which is inside the crypto boundary and also the crypto algorithms, that should be authenticated, or only authorized interfaces must access this crypto boundary. So in that case, even the speculative execution that cannot access the memory or the key if it is inside the crypto boundary, if it is properly implemented. So in that case, the 19790 is really covering many of the vulnerabilities, but still, as you likely said, there are many other attacks, so which can also be included into the standards. But totally, now we have only 11 security requirements, so tamper and those interfaces and all. So now side channel is also added into it. So recently in last 5 to 6 years. So we need to actually evolve. Having in mind, crypto accelerator is not only the security component. We should actually holistically see the complete architecture and then draft the policy, security standards. So that really will work. We need to add more security evaluations into the architecture level. That is not totally covered. Only it is a crypto level it is covered. But architecture level, we need to have a policy, yes.
Right. So, like speaking of security, right, problems in security range right from the hardware, like the side channels and fault attacks, right, which is mostly hardware centric. But we also have a lot of software level security issues, like the things related to control flow or bypassing or buffer overflows and things like that, right? And what we have seen is sometimes like processor manufacturers try to address some of these concerns in hardware, while the other times they say, we don't care about it, let the software handle it, right? So where do you, and specifically because silicon is not free in terms of area, costs and so on, so the more you actually push into the hardware, the more expensive your chip actually gets. So where do you essentially draw the line, or where do you decide, maybe Saurabh, that's one for you, where do you decide what should be handled in the hardware and what you don't care and let the software guys do it?
Yeah, I think it depends on the domain where you are actually selling the chip, right? For example, speculative based attacks, they are only, I mean, they will occur only in very large out of order processors. And if you are not in that domain, you really don't need to worry about it. If you are an in-order core, say a 5-stage RISC-V core, there is no chance of having any speculation-based attack. But if you have like hundreds of in-flight instructions and you have some leakages in lots of drivers, then this is a problem. So similarly, but if for the other extreme is, you may have very small cores which are not out of order, but they may be like used in, say, your payment system. So there will be a lot of attacks on those. And like in NXP, we sell a lot of these where they're directly attached to the payment systems. There are software attacks. So like control flow integrity is something we do a lot in those chips because this is very common. There are physical attacks also. Physical attacks is almost gets you very similar stuff, but there are tricks to do it. But sometimes the physical attacks are easier to do because you in a big server, you can't have access to that server physically. It's in a big room guarded by security. But if it's some small device and it's a payment system, people can try a lot of stuff with it. Like we have seen people trying clock glitching, power glitching, electromagnetic radiation. So all these type of attacks need to be taken care. So I think what happens is when we look at what is the market that this is going in, and typically there you have to address is yes, normally for general security it's okay. You have memory isolation and privilege levels, those are basic things. But for these type of attacks, especially the side channel attacks, you need to have an understanding if your target market would actually be doing that side channel attack or not. In many cases, it does not make us, like for example, the markets we play in, we will not face any meltdown Spectre type of attacks, but we will face a lot of physical attacks. People take the device, try all the types of radiation and all those, and then we need to put in control flow integrity plus more above the normal RISC-V control flow integrity. The normal RISC-V control flow integrity is software attacks, right? Say return attacks or indirect function attacks. But you can have physical attacks like skip PC. So you skip the function call that is your authentication, and people are expert in doing that. So we have to put in those type of features.
Yeah, so just to extend that question, right? So let's say since you spoke about the instruction skipping, which is mostly a physical attack, so do you decide to actually put a countermeasure in the hardware, or you could also maybe have redundancy or maybe put some error correction in the software, right? While so how do you decide to put a particular countermeasure in hardware versus add it or put it, make the compiler as such, software compiler essentially handle it?
Many of these physical attacks, what I have seen is the countermeasure is in the hardware, because that's safer. What the software, the tool chain changes obviously, because you have to instrument a lot of code differently and stuff like that. So you will have, say, GCC or LLVM or whatever, you will have your own libraries and own compilers, and we do work with some vendors to work on those things. But many of these physical attacks are actually taken care by hardware countermeasures. And what changes in the software is the tool chain and how you write the software on top of that. Those will not be like vanilla, how we write normal software. There will be some extra attributes. There will be some extra stuff in the compiler which will put in new instructions, all these things. Like for example, like I can talk freely about the normal extensions in RISC-V, like you have landing pad or these you need to basically have that extra compiler support for that, right? So those type of things are there. But hardware countermeasure is much more safer.
Do you have any additional points?
Yeah, I think there's no simple answer to it. I think the answer will be in multiple folds. The very first thing is that when you think about any attack, you first have to go and really understand what the attack is. And at times it just turns out that, like you mentioned, right, the fix has to be in the hardware and you cannot do anything in the software. So yes, there you don't have a choice but to go ahead and put it in the hardware. Now, for a particular solution to even work, there's also the notion of performance hit, right? I mean, if you want something to be done, almost always you may want to still put it in the hardware. You can do it in software, but because it's just done so often and it will consume so much of power or so much of CPU time, it may make sense to just put it in the hardware. That depends on the type of the attack. But I think at the end of the day, all of this just boils down to math, as in how much money would it take to put it in the hardware versus what if you don't do it at all? Because at the end, like you mentioned, there's only limited silicon area, right? And silicon area is really useful. So if you can get away with it at the software level, and maybe some of these attacks are not even that common, and even if it is probably not that critical. You can, and that's a soft call that companies make, right? Where you say that this is fine and just don't do such and such things. You will have erratas documents that say that, don't do this. Does it have some resistance from the user? Probably, but it'll work for 95% of the use case, and for the rest 5%, the customer will have to do something special in order to prevent that attack. So I think it's a mixed solution.
Yeah, I think if it can be done in software, do it in software should be the knee-jerk reaction for anybody, because it's easier to change, it's easier to verify. Hardware can have subtle bugs that the more hardware you add, the more of a headache it is to verify, to validate. So my first reaction is always do it in software, see if you can actually make it work. Sometimes you have a hardware attack for which you have a software fix. You have a software attack for which you have a hardware fix, like landing pad. You have to mix and match all of these things depending on the mission profile. I think you were talking, sir, about many of the very small devices where the software is just not capable of even, you can't even run enough software to get to the point of mitigating that attack. Irrespective of, I mean, the next question is if it's possible to mitigate the attack with software, but there is just not enough compute to do that. You add more compute and you're making the device too expensive. So things which never change are smaller to do in hardware than to do in software area, and things which going to need anyway all the time. I think mostly you put those in hardware, and that this is not even a RISC-V question, right? Countermeasures like glitch detection and so on. It's not even necessarily a RISC-V question. It's just things that you sprinkle across the hardware.
One thing I should mention is like for things like speculation-based attacks, software fixes are more common. You have serialization instructions, synchronization instructions, so you do a knee-jerk reaction, block it there so that it doesn't speculate beyond that part. So you will have a lot of people doing software fixes, and it's common, and especially with the speculation-based attack software based fixes are pretty common. I think that's what even when they were all Meltdown Spectre came out, they were doing basically software fixes so that people don't run into it.
Right. So let's change track, right? So there's a focus on security, but also in the symposium there is the AI as well, right? And I don't think we can have any panel discussion with it without bringing in AI. So where do you think AI, or how do you think AI will actually change security, right? Or specifically for RISC-V. So I know that AI could help the designer as well as the opponent also, right? So I think most people believe that the opponents or the adversaries are more benefited by AI, right? And we on the other hand are designers. So where do you think AI could help or / affect?
I remember reading a quote very long back. It is a power that can only be used for good or evil. So it's never going to lie unused. Somebody is going to try to use it, and somebody is going to counter with the same thing. I think what we've been seeing of AI-enabled attacks on things, and especially very often now what I'm hearing about is AI attacks, which like what happened with the OpenAI and Hugging Face very recently, right? Something that's not even realized that it's going on until it goes for a while. The nature of LLMs is to be stochastic and unpredictable. And I'm very scared to say integrate an LLM into an pipeline, into a security pipeline and rely on it. But using them to narrow the search space and using them to find those points of attack. I think getting about 80-85% of any kind of problem solving is, any kind of debugging is finding the problem. And I think when you use them there, it's already showing a lot of promise in the way that we go about finding those things. But then there is a danger of getting inundated with low-grade, spurious attacks which don't really matter. So a little careful to be.
So I have different perspectives on this. The very first thing is that because you now do have AI, people are talking about a future where you probably will not even have the 100 apps that you today have on your phone, right? It may end up to be just one agentic interface that you talk to, and you order shoes, or you order bananas or whatever it is. It will be just one interface. So I think first of all, when the interface itself is very small, the amount of backend code that exists is also small, and hence the attack surface itself reduces. It's possible that you do see much lesser attacks, at least on mobile phones. That's one perspective of how AI may even AI changes the way we interact with people or with anything in the world. But I think specifically with respect to RISC-V, like you mentioned, there are a lot of small devices that will come up, right? That detect and that'll probably be running small models. So I think forget even the small models, or whether it is you using an AI agent. For example, today almost everybody uses some agent, say Cloud Code or Codex or whatever, right? The hacker, it is very easy for a hacker to just try to attack and get these API keys that you use for accessing these models. All of these big companies, they are using tokens close to $1 million almost every month, right? They're burning a lot of tokens, and if you can just get that one API key, you can go ahead and access all of those. You can go ahead and access all of those models, and the company and some other company gets built, right? I think there is no standard way of really protecting the API tokens, for example. That is not standardized today. Of course, if you're talking about normal passwords, those are kind of standardized. You either remember it, or you have something like Google Password Manager, which is hopefully secure to some extent, right? But API keys is usually just copied, and if it is not Google Password Manager, people just use Notepad to paste something. They don't really have a vault or something where they really store API keys. In fact, there were one of my friends who is currently running a startup. He actually did this, and they lost $100,000 of AWS credit. And this happened like 2-3 weeks ago, right? So this is a real threat, and that is happening. So that's one side of the story. Another side is, especially in the small devices, right? I think that is where RISC-V will make a difference, where people may want to go ahead and implement different types of security solutions. They may customize something, or they may want to put something that is very optimized for that particular use case. And that today only RISC-V lets you even experiment with such use cases. Of course, ARM may come up with something, or x86 may come up with something, but that'll be hard-coded for something. It'll be hard-coded to what they think. You cannot go implement anything. So RISC-V will help you come up with new solutions and really innovate on edge device security.
Yeah. So we have a poster in our stall where we demonstrate a very similar small device, a sensor chip, where you are using an AI model to basically detect a security attack. So it's basically some capacitance profile, it will be like that, and under noise and all those, you train the model, and then it's not a big model, as he said. These are like small models, and when there is an attack, the AI model is able to pretty much accurately predict. So these are all in experimental stage, but we are working on these type of things that AI helps security. And with RISC-V being open source and all these, this is becoming more and more feasible. That's the good part of it. Of course, it sometimes can hallucinate, and so you have to basically decide on how many false negatives you can take, how many false positives you can take, and you have to build all those systems. On the worst side, with these AI tools, the attack surface has increased tremendously, because you are basically what you could not do manually by just running some of these very powerful AI tools. They can just go and look at each and everything, whether it's RTL, whether it's a photograph of your chip or whatever, right? They can really give you huge information. And we're seeing the capability of some of these tools. It's enormous. And so that is obviously quite a big threat, that with the help of AI tools, the attackers or the malicious people who are skilled, they may be able to exploit it much better than earlier days where something was hidden, nobody found it out for 10 years, right? That will not happen. The attackers will use the AI tools very quickly, and there will be new types of stuff going on now between the attackers and the defenders. Both of them may be using AI. And so that's a very interesting thing that will happen. When the attacker also uses AI and the defender also uses AI, who wins? But I think this is something we have to learn. I mean, we are just in the beginning phases, but there is no denying the fact that this AI revolution, the power is immense. It can just scan your RTL, thousands of lines of code, and easily tell you within minutes there is a security hole, right? So these type of things, if you had to do manually or through certification, would take months. So we have to be careful. Plus, the third dimension comes is we are now using AI tools in chip design a lot. We are relying on AI tools to do our verification plans. And so it's not always feasible. We always tell the teams, go and manually detect or put a validation step even with the AI tool. But there will be slippages because you have a 100-member team. There will be lazy people who will not do that, and things will flow through, and the AI hallucination will create more problems. So this is the third angle that we are now having to face, that how do you manage big chip designs with all the AI tools that the quality doesn't suffer. We get tremendous efficiency boost, but with that efficiency boost, we now get lazy. And then things start flowing in one of those scenarios where you miss a bug.
Yeah, I will add one thing. So instead of developer and adversary, so the evaluator also is AI empowered. So in that case, we also use AI-assisted side channel, AI-assisted LLM-based vulnerability analysis on source codes. So who is powerful? That's the question. So as you likely said, if the adversary is very powerful and he has a very powerful model, he will be able to catch up. But the evaluator and the developer are in the same side. So they can be more powerful than the adversary. So if they work together. So definitely AI is making a big changes in the designer perspective, attacker perspective. And if we work in a planned manner, definitely we'll be able to develop a very secure module. Yeah.
So thanks. I think we do have a few minutes for questions from the audience. Pass on a mic.
Hi, I'm Atul. I lead the RISC-V architecture group in Qualcomm. So I just wanted to ask a couple of questions on, so you say RISC-V security extensions, right? One of the pain points that we always saw was, if you say the lightweight security extension group, it has been taking quite a while to standardize, even the simplest things as RISC-V worlds, right? And if you go to the AP side of things, there's the supervisor domains, the SMMTT or SMMPT has been taking ages just because one of the companies decided they won't support it anymore. And it's been dragging. So the question I want to ask, how does that impact, say, a startup scale or a huge company, and how do you deal with it now?
So this is one of those places where the fragmentation does hit us. And what happens is typically when you have these kind of situations, the standard is not evolving fast enough, people come up with their own solutions. And those own solutions can end up becoming de facto standard, but then they're not the standard. And then you have people who come a little later and adopt the standard, and then you have the fragmentation going on. It's a painful situation generally. I have a certain philosophical disagreement with the way that some of the the crypto standards have evolved in RISC-V, but I mean, that's not for me alone to legislate over here, is it? So, and this happens with any standard where you have multiple interests competing. You have many people with different perspectives and different needs, and they're trying to get everything into the standard. It's pretty common. But I think, going back to our last question about AI, I don't think we have the leeway to take 3.5 years to ratify a standard which needs to go in 3.5 years into chips. So maybe we need to speed all of this up.
So, any other questions?
So maybe from my perspective, I would say don't wait for the ratification. So because that is not in your hand, it will, as he said, it may take several years. So it's okay to be a bit non-compliant or some encodings change, 10 more instructions get added. But it's very important to hit the market with your product to actually make a difference, right? So we cannot wait for ratification in those cases. You, more or less, you know what those extra holes are. Go ahead with that, and I think you guys must be doing similar stuff. And when the ratification finally comes up, in your next revision, you make it compliant. I think that's what typically most people will do, trying to get into a new extension.
Are there any more questions?
Hello. This is more of a generic question with respect to usage of AI tools. Like, how do you make sure, like, you, like, the proprietary IP data and all is not leaked on, let's say, when you're using Cloud Code or Codex? Like, how do you make sure it doesn't get leaked?
I mean, the short answer is you don't. I think unless you are developing something that is truly out of the world, you should probably protect that. But I think as a startup, at least what we are doing, I wouldn't say that we are really reinventing the entire wheel, and this is something that nobody else in the world can ever do. Cloud Code already knows whatever we are trying to build, most of it at least, right? There'll be some things here and there. That is not the primary concern that anybody should really have. I think you should adapt. Of course, if you're $1 billion or a multi-billion dollar company, Cloud Code will give you a opus and you can run it on your own server and you can train it on your model, even fine-tune it for yourself, right? But that's a multi-billion dollar company thing. For startups, I don't think you should really worry about that. Tech moat is really reducing, right? In the age of AI, anybody can build anything. You just have to prompt the AI correctly to be able to build that product. And whoever moves the fastest is going to be the winner. And of course, for a startup, it is not just going to be that particular implementation that really gets you customers, right? It'll be the idea, it'll probably the way you market, customer support. There are like 100 other things that you'll have to focus on. So specific code and tricks, and I think Claude already knows all of that. You should probably not try to hide anything from it.
Yeah, and just to add to that, I think, tech moats were a very fleeting period of time that you could actually just say that I have a technology which is so unique that nobody else can build it. I don't think we're in that world anymore. So trying to keep that held very close to your chest is not really getting you anywhere. But on the other hand, there are other modes that you can build. And on the other hand, there are some things that I don't trust, because the other problem over there is not, the flip side of the problem is not, can I trust it to hold my code secret? The flip side of the problem is, who else's code is it shoving into my implementation? And that's a really hard question that opens you up to legal liabilities and things like that. So it's a scary proposition, and I don't have an answer.
Hi, my name is Sumit, and I typically come from a training organization where we take up a lot of trainings and extensions. How do we deliver to the working professionals? So my question is typically nowadays, although vector extension is one of the very talking point on RISC-V, whether we are going for AI accelerator or something related to cryptography. But there is also something like somebody told in the panel, like scalar based cryptographic extensions, where you might not rely on a vector extension to actually provide cryptographic services, typically provide to microcontrollers like 32-bit microcontrollers and those kind of services. So maybe is there any future, are there any real scalar extensions based cryptographic services which we can work on RISC-V typically for 32-bit systems, means typically for microcontroller based SoCs? Thank you.
Yeah, so one thing that is missing today is side channel resistance, right? You can probably propose an extension where you have these instructions that are also side channel resistant. I mean, which means that it's not just functionality that you care about, but you'll also have some details on the implementation of the actual instruction. So that could be another scalar. Specifically, if you want scalar, then that could be one extension.
To a certain extent, I think the existing cryptographic extensions are scalar, and then there is a vector crypto. So you can actually choose. But like Arjun said, I don't think it says anything about side channel. Yeah.
So I don't know if the post-quantum crypto has got ratified or anything. So yeah, so that's definitely something coming. A lot of people are working on making their systems quantum safe. So I think that is quite a hot ratification people are waiting for. I mean, when it finally gets ratified. But other companies like we are going ahead with our implementations in the meantime.
So, yeah, since there are a lot of students, just one generic question to everyone. So let's say there's a student maybe in the first year or second year of college and interested sometime in the future to take a career, right, in security and hardware. So how do you think they should essentially prepare? What are the skills, both hard, like academic as well as soft skills, one should essentially obtain to go into this direction?
Yeah, so if they want to pursue their career in hardware security, then I would always suggest to focus mainly on the architecture level, then what are all the security vulnerabilities in advance. So their basic curriculum covers all the hardware aspects, I hope. So in that case, security, they have to actually focus on all side channel vulnerabilities or any vulnerabilities that hardware, you have to be updated with all the things. So you can register into many of the forums available now. So Hardware IO, so many of the forums are available. You can get registered, update yourself and prepare yourself. So
I think the most important thing for any of these kind of things, the best thing that teachers is doing. So get hardware, play with it, recreate attacks. Try to block those attacks, work with a friend, have one attack and one defend. I think those kind of things really work.
I think there's so much of information available now, right? You have OpenTitan, you have Calyptra. You should just go try to understand what have people done today, right? And these are industry grade systems. These are not just certain, it's not like an academic thing where they just teach you basics. Of course, basics are important, but that is no longer sufficient in today's world, because you have all of these LLMs that can do all of this in a jiffy, right? It is really important to understand everything at a system level, and that is what OpenTitan and Calyptra will let you do, because they have really good documentation, which was missing in an open source implementation for a very long time. Second, you should also really use AI tools to understand all of these things, right? Feed in the code, you can, whatever you don't understand, just keep keep diving deep into it and keep asking the LLM questions of whatever it is that you don't understand. I think if in general, if you're able to understand any complex system, it need not even be security. If you guys are interested in anything else, whatever it is that you're interested in, you should pick something that is complex in the domain that you're interested in and try to understand whatever you can of it, right? The moment you start understanding big complex systems, that is the primary skill that you need today, right? Tomorrow, no matter what job you're doing, you need to have the ability to think at a broad level, because LLMs will take away all of the lower level jobs. That will all be agentic, right? Your job will primarily be able to, one, prompt the LLM, and second, more importantly, which I think is not really happening today, is you should really critically analyze the output of an LLM, because 80% of the time it is right, but 20% it is wrong, right? So you really have to have the knowledge to say that yes, what it is saying is wrong. So yeah, that can come only when you look at big systems and you try to understand everything from a pretty wide perspective.
Yeah, I think I would say if you are an undergraduate, you should focus more on the basics. I think having solid basics in your core engineering disciplines, maths, physics, these are very important. This is the one thing that will help you to become an architect or the guy who can understand the entire system very well, which even the most powerful LLMs cannot easily understand, because it takes like 20 different contexts to actually understand a problem, and that is where the value will come in. So it's very important that we build the basics very well when we are in undergraduate. Once you go to postgraduate or PhD, then you do specialization. And obviously, those are a different kind of study that you have to do in your field. And of course, the usage of AI tools is must. But when you are, so that you get used to it, right? So that you know how to prompt them, what makes sense, how to build agents, how to build some real flows around it. So how do you automate your tasks even when you are a student, right? This will help you later on in the industry where you have to do the same thing. But I think as an undergraduate, I think most of the guys here are undergraduate, it's very important to get the basics extremely strong, because that will make the differentiation. A guy who has strong basics versus whose basics are not good, the former will always be required even in an age where LLMs will take over, right?
Right, so thanks. I think we've just run out of time. I think it's a very interesting situation. So we are, like we started off, right? So in a point where what open source has done to software, we are at the point where RISC-V is essentially doing for hardware. And I think 10, 20 years down the line, I think it'll be very interesting to see where this essentially takes us, right? So hopefully we are able to build systems that are inherently secure. One critical aspect is that we should be able to build systems that are not just secure for the attacks that we know today, but also attacks that can potentially come later on, right? So thanks everyone for joining, and thanks my panelists again. It's an excellent discussion. Thank you very much.
Thank you, panelists, for that insightful session. I now request Professor Chester to felicitate all the panel members. Chester sir will now Shri Saurav Roy sir is now being felicitated. Next up, we have Suganya ma'am being felicitated by Chester sir. To felicitate our moderator, Professor Chester, I now invite Professor Patanjali to give a token of appreciation. Thank you.
Before we move forward, we want to take a moment to express our deepest gratitude to our sponsors. Their visionary support is the backbone of this symposium. It is their commitment that empowers us to bridge the gap between academic research and industry reality. We truly appreciate their role in taking the ecosystem forward. Thank you. We'll now be hearing from our industry partners. We would like to introduce our silicon sponsor, Mindgrove Technology. Mindgrove Technology is an IIT Madras incubated, Chennai-based fabless semiconductor startup founded in 2021 by Mr. Shashwat ER and Sharan Srinivas J. The company designs high-performance, cost-effective systems on chip and microcontrollers built on the open-source RISC-V architecture. I would like to invite our keynote speaker, Mr. Kapil Sham from Mindgrove Technology. He will deliver an address on the title, Concept to Certified Silicon. I'll be introducing you. Kapil Sham M is a founding engineer and system software engineer at Mindgrove Technologies, where he has played a key role in developing secure RISC-V based computing platforms from the ground up. His work includes secure SoC architecture, trusted boot and firmware, secure software, virtualization, and secure technologies for next generation embedded processor. Before joining Mindgrove, he was a part of the Shakti processor project at RISE-Lab IIT Madras, contributing to processor architecture and low-level software. His research interests span embedded system security, hardware, software, co-design, and automotive systems. With expertise across both hardware design and system software, Kapil is passionate about building secure, high-performance computing system that bridge innovation and real-world development. We are welcoming Kapil on the stage. Thank you.
Thank you for the warm introduction. So I would like to begin with, as they introduced Mindgrove already, and I just want to reiterate some of the things. So Mindgrove is a fabless semiconductor design company incubated by IITM Pravartak and IIT Madras Incubation Cell. And we do tape outs at TSMC. We did some tape out at TSMC 28 nanometer node. So we make chips for all the IoT kind of applications like biometrics, drones, metering applications, medical devices, CCTV cameras, and also automotive applications. So, for some of the people who don't know, the chips which Mindgrow builds are on top of the Shakti C-class developed at IIT Madras by Professor V. Kamakoti and the RISC-V team. We have had a 5-year journey of making chips. So, company was founded at 2021 by Shashwat and Sharon, as I introduced already. Now, in 2024, we have had our first MPW of the chip called Secure IoT, or S2401. So, in 2026, we are going into the commercial production version of the same chip. So, the commercial version, the chip which will be available commercially will be of two types, or in two packages called BGA 144 and QFN 64. So, those are the two packages available, and yeah. So, this is the feature list of the first product, Secure IoT. So, we have the Shakti C class with 16 KB iCache and 16 KB Dcache, and we have a huge memory of 128 KB SRAM and 8 KB of boot ROM, which is capable of doing secure boot. And also we have the XIP flash there, the quad SPI, which has the XIP feature in it. And also you could use the same quad SPI for increasing your RAM also, like you could add on the PS RAM. So we have both the supports over the quad SPI. And let me introduce security on the Secure IoT. So it's like we have AES 128, 192 and 256. And we have SHA-2 present there, SHA-2 256, and also RSA 2048 bits. So those are the core components which are used in the secure boot. And there we have a huge number of peripherals like SPI, I2Cs, GPIOs, UARTs. So many of them are pinmuxed, and you could use peripherals if you want, or else you could just have the pinmux option, so that you could have everything as GPIOs and try to bit bang whatever peripheral you want on the chip, right? So we have that feature here, and also 5 MSPS ADCs of 8 channels. And on the system side, we have a PLL, DMA, 8 DMA channels, and we have timers also, like general purpose timer and watchdog. And for interrupts, we have two kinds of interrupts, PLIC and sealant. Both are compatible with the RISC-V specification. And also we have the RISC-V debug 0.13, which was also from Shakti, and yeah, it's also ratified by RISC-V. And we also have RISC-V efficient trace, which is like ratified recently. And here are some glimpses of capabilities of the S2401 chip. So we recently got our production version of the chip, yet to be commercialized. The boards are like in progress. So these are screenshots of us verifying the chip. So we are able to run the post-quantum cryptography algorithms like MLChem and MLDSA, all the 3 versions. So MLChem 512, MLChem 768, and also MLChem 1024 were working properly. And also the MLDSA 44, 65 and 87. They were successfully done, and we verified the secure boot also, and it was also success. And we have dynamic frequency scaling. So as we already mentioned, Secure IoT is 700 megahertz processor, but if your application requires to run at low frequency, you could always trim down your frequencies. So that's why we have this feature here. And The status of S2701, the production is underway. We will have the evaluation board soon in our hands, and I hope you all will be able to order it online, right? Either in Amazon, Trovo, or whichever platforms you would like to. And we have an open source SDK. We will release the SDK soon with the evaluation boards. So we support FreeRTOS, Zephyr RTOS, NutX, RT-Thread, Cell4, and also PSA compliant APIs. So for people who don't know what PSA is, I'll come later to it. And we have support for IDE also, like Visual Studio Code and Thea IDE. And these are the customer verticals, as I already mentioned: biometric scanners, smart meters, robotic controllers, educational boards, etc. So we are planning, since we have all the security features also, we have to get it certified. So we are planning for ISO 19790, which I'll again tell in more detail soon. This is our second product, called V2600. This is part of VisionSoc series, and it will be clocked at 1 GHz to 1.2 GHz with all the FPU and with the vector RISC-V vector extensions, 128-bit vectors. So it will have H.264 and H.265 encoder. It will have an ISP on the hardware itself, and it has two MIPI CSI channels, and same QuadSPI based QuadSPI or OctaSPI based flash and PSRAM support will be there, along with the gigabit Ethernet. So on the crypto side, we have AES, RSA, SHA secure board, and it will add another cryptographic module also called the ASCON. So it is the recently certified lightweight cipher by NIST. We'll be having that on the hardware also, in addition to which we had already. And as mentioned, this will also have PQC running as a firmware. We have OTP memory also in both the chips, so for storing all the keys required. So capabilities for this V2600 include IoT SCS compliant HSM, which is a dedicated secure core for it, and it has an ISP video codec, and it's a dual issue version of the Shakti C class. So what was implemented on the secure IoT S2401 was a single core, single issue in order pipeline, but this will be a dual issue version of the Shakti C class with all the vector capabilities. And multi-core version will also come along with the Vision series. So yeah, and along with that, hypervisor is also under development. So okay, let me move on to today's agenda. Like since the topic says concept to certified silicon, we'll have building, standardizing and securing the hardware. So these are the three closely connected aspects of modern chip design, and now we will look into it. So here is the thing: security is not something which can be bolted onto the silicon, but needs to be baked in it. So instead of treating building and securing as two different topics, we'll combine them together and look at 7 core design principles which help make systems fundamentally secure. So the first principle will be the principle of least privilege. So give access to something only till someone needs to complete their job, not to everyone else. In RISC-V, we have different privilege levels. such as machine mode, supervisor mode, and user mode. And in embedded systems, we commonly use machine mode and user mode. So machine mode will have the complete control over the hardware, like memory, interrupts, security configurations of all the cryptographic accelerators, whatever you have, the entire control over the memory map, right? But the normal application should never run in machine mode. They will always run in user mode, which doesn't have all these access. So if you want to access any of the peripherals, or if the application wants to interface with the outside world, it needs to go to the machine mode, and then you could get the access. Because if the application runs in user mode, it has very restricted permissions. So if an application crashes or gets compromised, the damage remains limited to the user mode and will not affect the entire system. The next principle is called defense in depth. Never rely on a single security mechanism to protect the entire system. Instead, we will build multiple layers of protection, so that attacker has to break through several defenses before compromising the system. For example, in enterprise security, we combine identity access management, multi-factor authentication, unified endpoint management, network intrusion prevention systems, firewalls, vulnerability scanning, and also we'll have the encrypted data. So we have this long chain, which is very hard to get compromised. So even if one gets compromised, the attacker will get caught in the other part of the chain. So likewise, in secure boot, we don't simply store the firmware hash and then compare it directly. So instead, we would do RSA on top of it and store the cryptographic signature on the flash memory, and then at the time of booting, we would decrypt or verify the signature present on the flash memory. Then we will compute the hash of the application in runtime. We would compare it, and then finally we will say whether the application is compromised or not. So this gives you a good proof that the application is not tampered. So the third principle is called fail-safe. The fail-safe principle assumes that every system will eventually fail, because Murphy's law, right? So anything that can go wrong will go wrong. So in security engineering, we should never assume that software, hardware, or anything or the users will behave perfectly forever. Failures are inevitable. The important question is, when failure happens, does the system fail securely or dangerously? For example, if secure boot verification fails, the system should not continue in an insecure manner. Instead, it should just stop then and there. So a secure system is not one that never fails. It is one that fails in a controlled and a secure manner. The next principle is keep it simple, stupid. As like my CTO would love to include food analogy to whatever he speaks, like any of the concepts. So I would like to do the same like here. So when we want to go to A to B, like when we are in heavy hunger, when we take a drive to A to B, we don't like a lot of twists and turns there. So likewise, going from point A to B is not like should not be too complex for us. So for that, there is a law told by Bruce Schneier. The worst enemy of security is complexity. The more complex a system is, the harder it is to ensure that it's going to do what we want it to do. So what we need to do is make the system as simple as possible. The next principle is separation of duties. Imagine a door with two deadbolt locks and each with a different key. One user with one key and the other with the other key. In other words, what we have here is we have spread the ability to open these doors across two people. We do that because now it requires collusion in order to break into this system. For example, in secure boot, one entity may generate the firmware, meanwhile the other securely signs it using an RSA private key. The device will trust the firmware only if the signature verification succeeds. By separating responsibilities, we reduce the chance of a single compromised component breaking the entire chain of trust. The next principle is transparency. So, as stated by Suganya ma'am, like security is not through obscurity. It needs to be, so everyone needs to be aware of what is present there. So, it is something which no one really tries to design into a system, but a lot of people feel secure if they think no one knows how their thing works, like the SOC works. For this, let me quote the Kickoff's law. A cryptographic system should be secure even if everything about the system except the key is public knowledge. So, I think we all agree with this, right? So, if we can't really look into what's happening in there, then we can't tell if the algorithm is good or not. Then it raises immediate security question whether it is secure. So, we should not have that question at all here. And the next thing, at the end of all of the security chain, right, it is a human present there, and humans are almost always the weakest link in that chain. So, here what we need to be really looking into is the usability. There is a good example of how security department has made the things difficult, and as a result many things were less secure in the way they designed the system. So we put the requirements like the password needs to have some uppercase characters, lowercase characters, numerics, special characters. It needs to be of certain length. It has to be unique and also fresh, which means needs to be updated in a kind of time interval. All of these things would go into what should theoretically be very strong and secure password, but what the end users do when they have a look at all of this, turns out there is a solution called, like I have put a sticky note here, but it's usually a password manager. People use sticky notes or write it into some paper and store it somewhere in their house itself, or they would use some kind of key or password storing extensions on the browsers, etc. So this password storage device that users turn to, and they put all of these things on their monitor, thinking that no one will ever suspect to take a look at it. And it won't matter how strong the password rules are if people end up doing this. So if you make a system too hard to use, then you have created an insecure system. These are the design principles which I would recommend everybody to follow while designing a secure cryptographic system or a secure SOC or whatever. So this is now we have designed a system, a secure system, but how do we prove that to the customers that the system is actually secure? So for that we need to have some kind of attestation with it, like we would have the certifications for it. Like for that we have three parts: CAVP, ESV and CMEP. So for there are ISO standards like 19790, which is effectively aligned with the FIPS 140-3 certification ecosystem, which is highly developed in the US and Canada. The process starts with algorithm validation through CAVP. CAVP means Cryptographic Algorithm Validation Program. So here the algorithms like AES, RSA, SHA, ECC, every algorithms are verified themselves against the NIST test vectors to ensure that the correctness and standards compliance are present. Since all the cryptographic activities depend on randomness, the entropy source or TRNG is independently evaluated to ensure that randomness is statistically strong and unpredictable. So that's where the ESV comes in. And finally, we will have the cryptographic module itself verified, called CMAP, Cryptographic Module Validation Program. So there we will have hardware, firmware, software, key management, secure boot, access control, physical protections, self-test, everything. All of these things will be evaluated together. The testing is performed by accredited laboratories like SETS, STQC, etc. And the reports are reviewed by the certification authorities like NIST and STQC. The actual testing may take only 2 to 4 months, but the entire certification cycle can easily extend to 6 months or even more because of documentation reviews, evidence collection, repeated clarifications, queue delays, and coordination between labs and certification agencies. The testing involves procedures listed in ISO 17825. That is another standard which is for all the non-invasive attacks, like for specifying how the side channel needs to be done, analysis needs to be done. So currently the certification evaluates the final delivered system, but many vulnerabilities actually originate much earlier during the design or synthesis or physical design, or while firmware integration or in supply chain handling. And I believe the future direction should be continuous certification where security evidence is generated automatically throughout the development, making the certification faster, more scalable, and much more engineering driven. And I'm going to highlight just one more standard in view of time, and it's about the PSA, which I told earlier, Platform Security Architecture. So what is PSA? PSA is a framework for building trusted IoT and embedded devices. So it takes care of all the firmware stuffs. So why does that matter? It has standardized security architecture, reusable software ecosystem, easier certification path. PSA is important because it has standardized not only the hardware security but also the software ecosystem around it. So when you write cryptographic, the driver for your cryptographic accelerator, there are certain rules specified by the PSA, so that if you follow all those rules, you don't need to make any additional efforts to make your software secure. All the PSA APIs will itself take care of all the security for the drivers. So PSA has created a common framework that the industry could build on, that significantly reduced the fragmentation and accelerated adoption of the secure embedded systems. But what are the challenges here? One of the biggest challenges today is that PSA has created a very mature ecosystem around ARM, but an equivalent industry-wide framework does not fully exist for RISC-V. And I think RISC-V needs this kind of framework, or the same framework can also be extended to RISC-V, so that nobody has to reinvent the same wheel. So like even though RISC-V has strong architectural security, like PMPs, ePMPs, crypto extensions, WorldGuard, and hardware isolation mechanisms, different companies build different secure boot architectures, different attestation flows, different firmware frameworks, and also different crypto abstractions. This means that the companies often end up solving the same problem again and again. So there are several emerging initiatives like Open Titan, which was already discussed in the previous panel by Chester sir, like the Open Titan, Keystone, confidential computing efforts, everything. But the ecosystem has not yet fully converged into a single globally adopted framework similar to PSA. So I think this is a huge opportunity for the RISC-V ecosystem and for the organization involved in the standards development, because the future of trusted silicon ecosystem will need not only a secure hardware but also a standardized security software stack, reusable trust frameworks, and scalable certification methodologies, so that the certification will also be faster and time to market for the chips will be like very soon. And thank you for the talk, thank you for the opportunity, and Jai Hind.
Thank you, sir. I would now like to request Professor Chester to felicitate the speaker with a memento. We would like to thank Mangrove Technologies for being the silicon sponsors of this symposium. On behalf of Mangrove Technologies, we would like Kapil sir to accept a token of our gratitude. Thank you, sirs. To introduce our next speaker, I would like to introduce Srimati Garima Jain from L&T Semiconductor Technologies. To a little bit about the company, L&T Semiconductor Technologies is India's first major fabless semiconductor product company, operating as a wholly owned subsidiary of Larsen & Toubro. It focuses entirely on proprietary chip design, advanced architecture, and IP creation, and also in creating smart devices and MEMS sensors for global markets. We'd now like to invite Srimati Garima Jain ma'am. She brings over 12 years of cross-functional experience, bridging the semiconductor and automotive industries across both hardware and software domains. She began her career as a design engineer at NXP before earning her master's degrees from IIM Bangalore. Since then, Garima ma'am has driven business growth through roles in business development, GTM strategy, product management, and strategic partnership ecosystems. Her versatile career spans leading multinationals, including NXP, Aptiv, Wipro, and Accenture, as well as innovative startups like Mangrove Technologies. She currently drives product management for the Compute BU at L&T Semiconductors. We welcome you, ma'am.
All right, thank you. Thank you very much.
Use this. Yeah, you can use this to.
So this is the click. Yeah.
Below button is the previous one.
Okay. All right. Thank you. Thank you very much. Okay. Hello everyone. Good afternoon. Distinguished dignitaries, esteemed academia, students, and my dear friends. Thank you for the really long introduction. And I think a lot more was said than I've achieved. But yeah, I'm representing L&T Semiconductors here on stage today, and going to be talking about our take on where the RISC-V ecosystem is, at least from the lens of an industry. So the topic of today's presentation is RISC-V at the crossroads of architectural innovation and ecosystem execution. This is the agenda, so it's a really small presentation. Over the course of the next 15 minutes, I'll be talking about what is happening in terms of the adoption of RISC-V cores across different markets. What is the impact of the type of compute that we are talking about and the kind of products that we are talking about? What is the state of this ecosystem? The state of this ecosystem itself. Is there a plateauing adoption? If yes, what is the reason for that? There is an illustration that I have of the automotive SDV software stack, mostly because I want to make a point that the real challenge is in the software ecosystem. That is where the gap is, and that is something which must be fixed first, and what must happen next, which is where we talk about how these gaps can be addressed. All right, so I'll get started with the presentation. Right, so like I said, we will be taking a stab at what is happening in the industry. So if you look at the slide, in moving from left to right, you're really going from some very basic embedded applications to consumer to industrial, then automotive, then servers, and then data center. So basically from left to right, what is happening is your compute intensity is increasing. And against each of these categories on the slide, what you see are the major companies in those areas. So, for example, I mean, it is very well understood that in the embedded space, there's a lot more crowding as compared to when you move from left to right, that is towards the data center, you'll see a lot less number of companies. So in embedded, you have Texas Instruments, ST, our own company, LTSCT, High Silicon, Silicon Labs, Giga Device, Mindgrove, Nordic, Unisoc, Infineon, Umbrella, Renaissance, Espressif. Consumer, you have a lesser number of companies. Then industrial, automotive, servers, and data center. Now, what I want to talk about on this slide really is, one, there are a lot of companies from amongst these who are using RISC-V cores today, but not as the primary core. So, I think we had Sir talk from NXP, wherein he did mention that NXP uses RISC-V core as the main secure core. Similarly, when you pick up any of these, you pick up Silicon Labs, you pick up Umbrella, any of these architectures, what you understand is the RISC-V core is not the primary compute core. It is acting as a system manager. It may be managing the communication between the safety island and the application cores. It may be doing a lot of other things, but not the main compute. That is the case with all the names that you see highlighted in yellow at this point on the slide. Now, these are what you see now on the slide, and it's pretty light if on the main screen. I have highlighted certain names in green, and these are the names which are actually using RISC-V cores, or they have completely RISC-V core based products in their portfolio. So Lendi Semiconductors is one, Unisoc, Renaissance, Infineon, Espressif. Some noteworthy names are Infineon and Renaissance when it comes to the non-Chinese counterparts in this view. Moving on to the next slide. Here again, this is a view in terms of the compute intensity. So if you look at it, it's really an alternative view from the previous slide, and the way to read the slide is really, one, go from bottom to top on the graph. So what you see is the bottommost layer is the MCU, then come your monolithic SoCs, then it is the chiplet architectures. On the y-axis of the slide, you see performance scale in terms of KD MIPS. On the x-axis, you see software complexity, and from left to right, it's basic to extremely complex software stack. And the size of the bubbles on this graph really is the compute heaviness in terms of the tops, the AI inference, or in fact the training number as well, because we have data center also on the slide. So basically, if you were to go from the bottom left corner of the slide all the way to the top right corner, what is happening is both your computation scale and your software complexity is increasing. The point that we're trying to make here really is, if you think about the adoption and the penetration of RISC-V core, it is really concentrated in the bottom left part of the compute spectrum, and sort of decreases, sort of fades away as you move from the bottom left to the top right. Yeah, and there's specific examples. So on the bottom left, what you see are the RTOS MCUs, your IoT MCUs. And when you keep moving away, there are specific examples that, of course, have been taken. There are a lot other devices: smart cameras, auto MCU, edge AI, auto domain controllers, central compute, mobile application, and data centers. Those are the ones that have been talked about. And really, the takeaway is what I've already mentioned, that as software complexity increases, as the software becomes more complicated, the RISC-V adoption is sort of on the lower side. This is a view of the RISC-V vendor ecosystem. So it's a limited view. I wouldn't really claim that this is exhaustive in any sense of the word. But what you see here is really, again, look at the y-axis. It says inception, growth, and then the consolidation part of it. More or less the point is, most of these companies that have come into inception have been consolidated one way or the other, and within, I would say, 10 to 15 years of their inception. And so again, if we look from the bottommost part of the slide to the topmost, what you just follow the journey of any of these companies. So you could look at CodaSip, for example. So CodaSip came into inception in 2014. In about, I think this was in 2022 or 23, that CodaSip got an investment of about 40 million. And then by the year 2025, I think this was in 2026, CodaSip actually gave away some of the RISC-V cores to onsemi, and right now they are focusing on the security-heavy RISC-V cores. Similarly, you pick up any other company, you pick up TenStorrent. TenStorrent came into inception in 2016. It was one of the fastest growing companies in the RISC-V space. From 2016 itself, it started picking up investments from the market. And if I'm not mistaken, it has gone up to Series D investment and raised over 1.5 billion in all these years. And now, now is the time when TenStorrent is probably on the verge of an acquisition by Qualcomm. That's at least the news in the market. So, yeah, so really this slide is about the consolidation, which is happening more like a phenomena in the RISC-V industry. This is just another view of the same thing. I was asking you to go through the journey of any of these companies. These are the individual journeys. This is the kind of growth trajectory or the consolidation trajectory these companies have taken. So clearly there's a pattern. Clearly this is what is happening in the industry. And what remains on the slide at this point, so that is Andis, Sci-Fi, Vincore, Condor, CodaSip to some extent, MIPS mostly because Global Foundries is still continuing the RISC-V core business of MIPS, and TenStorrent because it has not been acquired, it's still just news. So this is what remains in the market. This consolidation trend is something that is going to continue, mostly because RISC-V core, if you look at it as an industry, as a vendor ecosystem itself, was, and I could be wrong, I'm sure I can be, confronted with the opposing views here, but then RISC-V was not meant to be a core ecosystem by itself. RISC-V is supposed to be something that companies can use and make a part of their semiconductor design, but then they should be doing most of it themselves. So I guess that's the message that I'm trying to make in this slide. These are some of the challenges which are there in the RISC-V ecosystem as of today, and our respected speakers before this presentation have talked in length and breadth about all of this. So there's nothing new on this slide, absolutely nothing new. So you pick up one technical challenge, fragmentation concerns. I think this fragmentation word was used at least 10 times in the panel discussion. Commercial, think of the cost of migration. So anybody who has legacy code, so if you pick up an industrial company, the kind of legacy code that they have and the cost of migration that they see in moving away from an ARM core or an otherwise core to a RISC-V core is pretty high for them. Software stack, pick up anything, operating system for that matter. So operating system, when it comes to really commercial ISVs, the number of companies is pretty limited. So yeah, these are some of the challenges. And then I want to specifically talk about the main challenge in terms of the software stack part of it. We've talked about it since the morning. There's the hardware part and there's the software stack piece of it. And this is just a view of the entire software stack, so of automotive. So what you are seeing on the left side right now is the real-time cluster, and what you see on the right side is the application cluster and the possibilities in terms of. So on the left side, of course, it's the possibilities, because you can either have a classic AutoSAR or an RTOS, and on the right side, what you see is the way a hypervisor can divide the compute and have all kind of different kind of OSs resting on this. I'm just bringing this slide up to show you what is the complexity of the software ecosystem in a system like an automotive SoC. This is not an automotive MCU system, this is an SoC. So fairly complicated unless you have answers in each of those boxes, in each of those individual boxes. The adoption of automotive, of RISC-V cores in automotive SoCs is not far away, but yeah, it is at some distance from us. Yeah, so this is the point that I was trying to make when I was talking through the previous slide, that there are multiple challenges, and if you were to just pick up a few of the boxes from the previous slide, the maturity of the RISC-V ecosystem is sort of varying, right? I mean, right from being fragmented and limited and low to something that is strong. So on the compiler side, you're strong. On the ISA, it's of course, it is mature. But what really needs a lot of attention is the tools and frameworks, the OS part of it, and the middleware. Those are the three pieces which need maximum attention, at least at this point. This is the last slide. Like I said, these are the places where we see these challenges. Now, none of these challenges are, I would say, none of these are unsurmountable. So, for example, in the IDE, there are already open source IDE options available like Eclipse and VS Code. What is really needed is intelligent code navigation. So, with those kind of, these kind of things, your debugging of codes will become easier. Tools, like I said in one of my first slides, that right now RISC-V adoption is more of a phenomenon on the MCU side, on the SoC side, on the more complicated compute systems it is a little less. So by the time RISC-V starts getting adopted in HPC systems is where these tools and frameworks are likely to become, or likely to be more mature and make the programmer's job much easier. Similarly, OS RTOS, I was saying that when it comes to the commercial OS options that are available out there, for example, I know for a fact that QNX doesn't have a variant for RISC-V cores. Middleware, again, so better OTA frameworks are required. There's a lot more optimization that is needed than what is already existing. Compilers are there, but then with the latest extensions, there's still a need for a lot more maturity. Debug trays, BSP drivers, similar issues. Some of them are called out here. So yeah, this is all I wanted to talk about today. Thank you very much for your time.
Thank you, ma'am, for that insightful session. I now request Professor Patanjali to provide a token of appreciation to Garima ma'am. Thank you to both our speakers for those incredibly insightful keynotes. Your perspectives on evolving semiconductor landscape are truly invaluable. We will now take a short break for tea. Immediately after the tea, we kick off the highly anticipated Grand Challenge presentations, a showcase of the next generation of RISC-V innovation that you absolutely cannot afford to miss. We will now take a break, and we request you to be back in the auditorium by 5 p.m. so we can resume with the Grand Challenge presentations. Participants are requested to stay back in the venue. We have an exciting lineup of the Grand Challenge participants displaying their work.
Hi. We now move to the highlight of our evening, the Grand Challenge Hackathon presentation. We now invite Mr. Purushothaman sir to give a brief overview about the Grand Challenge Hackathon.
Hi, yeah, this Grand Challenge named GC 2025 is an initiative by Chip-in Center to encourage students to realize their innovative things into a startup. Okay. So this Chip-in Center made that proposal and it was approved by MIT and then IIT Madras and CDAC provided the necessary technical support. So when it was announced early last year, some 1,000 plus colleges all over India participated in that, and we screened them and shortlisted some 100 of them, and then those 100 teams were asked to give a proposal. From that we shortlisted 30 of them, and we have given FPGA boards and then asked them to work on it. And so they came up with ideas ranging from drone flight controller to some smart farming, etc., etc. Okay. So this was happening. It was spread over nearly a year, and initially we had a review for progress, and that was we called it a minimum value proportion, and in that we really checked how good they are doing and then provided necessary support. And one of the main criteria was they have to use either Vega processor or Shakti processor, our indigenous process. Okay, so it has to be based on one of these processes, and they worked on it, and then they cleared this MVP and then proof of concept. And last week we had final review, and in that they presented, and the first 3 teams are going to be announced by MIT. Review is completed, but the winners will be announced by the Honorable Minister. Time we don't know, but we have asked some 12 of the team. I mean, we offered the teams to come and present here. So some 12 of them have agreed to come, and 5 or 6 teams are going to present it today, depending on time, 5 or 6, and then the remaining teams will be presenting it tomorrow. Okay, so this is the background. We will have the presentation by the individual teams shortly. Yeah, thanks.
Thank you, sir, for that overview of the event. So let's now hear from the teams themselves. To give a brief overview of the first team that will be presenting, in the current market, all the drones and the flight controllers are imported from other countries. The upcoming team, Byte Gladiators, have built an indigenous flight controller using the Shakti RISC-V microprocessor architecture. They also have a startup called Chip UAV Systems that specializes in the same. I would now like to invite Shardul Bhave, Pranay Vani, and Rahul Desai from Byte Gladiators to showcase their project. Let's all encourage them with a big round of applause.
You can use this to change. Is it on the first slide?
Hello everyone. I am Shardul Bhave, team leader and co-founder and CEO of Chip UAV Systems, and team by Gladiators. With my team, I have Pranay Vani, who is also a co-founder and our PCB integration and system validation engineer, and Rahul Desai, who is our model designer and systems application engineer. So the main vision is that we should be building our own processor in the line of defense and UAVs. So currently in the market there are Pixoc and many other flight controllers which are using STM32 chips. So that is designed in Switzerland, manufactured in Taiwan, and then imported here. The basic essence is that if the imports were to be blocked, or we would have no chips or to fly our drones. So the vision is that it should be designed, manufactured, and fabricated in India itself. So that is what we're working on. And this processor, or Shakti processor from IIT Madras, gives us this opportunity because it is designed in IIT Madras itself. So currently, we are, as part of the Grand Challenge, we were given the RT board from the C2S competition, and we implemented a Shakti-based flight controller. We did some modifications to the core and some additions to the code to meet our flight controller requirements. And it's currently flying, and if the PPT is now showing, I'll show you the system architecture, some measured performance numbers, which is pretty interesting and very exciting in my opinion, because it is on a made in India chip, made in India processor design as it were. Not an ASIC currently, but it gives us a it is verified that it will work, right, on an FPGA at least.
while we are figuring out this technical aspects of the presentation, I request all the presenters to please occupy the front rows so it will be convenient for you to present next.
Okay, so now it's working. So this is our introduction. I'm Shardul Bhave, co-founder and CEO of ChipUAV Systems from Team Byte Gladiators. Along with me, I have Pranay Vani, who is a PCB systems and system validation engineer, and Rahul Desai, who is a model designer for 3D models and enclosures and lots of other things, including application engineering. So I'll just briefly go to the system architectures part. So this is a system architecture with the Shakti Yamuna SoC at its core, along with a custom Axi-4 Lite PWM IB. So that makes us a Vyom Chakra, that is our flight controller, as a flight grade unit. And along with that, we have our core navigation sensors, that is the ISM330DHCX, those are the IMUs, then the magnetometers, then the barometers. IMU for attitude estimation, magnetometer for heading, and barometer for altitude measurement. Then we have external communication sensors, which are a Neo6M, that is a GPS module, then an RC receiver for the pilot commands, and not volatile storage that is already on the FPGA chip that is used to store the calibration data as well as the program itself. Then we have expansion connectors. So Rahul will showcase the PCB over there, which will showcase you the expansion connectors that are already compatible with the aftermarket sensor modules that you get for PICSOC and stuff. So that being a standard, you can use any sensor modules already available in the market and just plug them in and it would work. So we have integrated that in our PCBs as well. Then we have support for 8 PWM based ESCs for driving the BLDC motor, along with power management with support for 3S to 6S batteries on chip. And then for ground station, we have USB for monitoring the sensor and programming the core itself. And also Windows app integration. So Windows app integration is also pretty interesting because it basically eliminates the need of the Ubuntu interface entirely. So the Ubuntu, currently, if you know, the Shakti core itself, if you want to build something on the Shakti, you need Ubuntu or a Linux-based system. We are using a WSL, which is a Windows subsystem for Linux. Along with that integration, you can program the Vyom Chakra and calibrate it so that you don't need a full-fledged Linux system. Next, we have some measured performance. So let's put some numbers on this thing. So a 250 to 500 Hertz configurable control groups tailoring to different airframes, and our altitude accuracy from our filters is about plus minus 15 centimeters, and a stable altitude flight that we have taken currently and validated is about 100 feet. We can go even further, but given the legalities, we couldn't, and that is what we consider safe at that time. And heading out accuracy is about 10 plus minus 10 degrees, and about 10 minutes of flight time using a 4200 milliamp hour battery. So the battery is user dependent. You increase the battery, you get more performance out of it. So we have a few specifications as well. So we are using PWM based EACs, and for GPS we have UART based. We can do up to about 10 Hertz. And batteries we have validated on 3S to 4S LiPo batteries, and the board is currently rated for 6S. And for RC, we are using FlySky's iBus unit, which is a widely adopted protocol. And for failsafe, we have some failsafes for prevention of accidental arming the motors. And frame compatibility is a huge one. We are compatible with the F450 frame, which is a beginner-friendly frame, and also a TBS 500, which is a dead cat frame, where the center of gravity is actually at the front of the frame. Currently on the screen, Rahul is showcasing the F450 frame with the flight controller at its core, and all the PCB is everything is inside the enclosure to protect the RT case, which is also very expensive, by the way, and to protect the insides also. So that's that. Then we have the PCB, which we already talked about. The expansion connectors are there, so you can plug optical flow module, GPS module, or power module, or a telemetry module directly to the PCB, and it will just work. So we are market compatible as well. And then I'll showcase the video.
Today, every UAV depends on a flight controller, and every flight controller depends on a microcontroller. Today, much of the world depends on foreign semiconductor supply chains. Many UAV flight controllers rely on ARM chips, technologies designed and validated through global ecosystems and manufactured through international semiconductor supply chains, including critical production facilities located in China. Now imagine a conflict scenario. A major disruption occurs. Semiconductor exports from other countries are suddenly restricted critical ARM-based components stop reaching manufacturers worldwide. But India continues forward because India has an indigenous alternative, Vyom Chakra, India's indigenous flight controller platform. At the heart of Vyom Chakra lies Shakti SoC, India's indigenous RISC-V processor architecture. Developed at IIT Madras, built for complete technological ownership. Fixed wing surveillance, logistics, different missions, one intelligent platform. A drone is just one application. The platform remains the same, one controller, multiple UAV architectures. Powered by Vyom Chakra. One processor, one platform, one indigenous foundation. Add more motors, expand the airframe, the intelligence remains the same. When global supply chains stop, India keeps building, India keeps innovating, India keeps flying. Vyom Chakra, powered by Shakti SoC.
So these are our some demo videos that we can show. This is showcasing everything that we have mounted on the drone. I'll just directly skip to the flights. So on the bottom right window, you can see the drone feed, and that's a ground station feed maximized. So what this FPV camera can do is basically do crowd monitoring, get into areas that humans could possibly not get. And this is a 100 feet altitude reach. And then we have another application for air pollution monitoring using MQ series sensors mounted on the drone itself. To be clear, drone is not going to be our product. Our product is flight controller, the basic brain of or the fundamental unit of any UAV. Yeah, that was it. Thank you very much. So if you have any queries, you can contact us on our website or our email. Our website is www.chpavsystems.com. On there is everything from our social media, our official email address as well. So you may contact us there. Thank you very much.
Thank you.
Thank you. Now we will move to the next team. All modern processors support secure boot, but the SHA-based cryptographic algorithm they rely on may become vulnerable as quantum computing advances. To address this emerging risk, PLL has developed a Shakti-based quantum-resistant security solution designed to protect system against future quantum-enabled attacks. We would like to invite the members, Soham and Dhruv, to do the presentation. Thank you. You can all clap for the presentation.
Okay, good morning. We are team PLL from DJ Sangal College of Engineering, and as quantum computers are on the rise, the need for security is proportionally increases. So we present our solution, which is hardware-enforced post-quantum secure boot solution for Shakti RISC-V SoCs. So this is designed to protect embedded systems against future quantum threats. So every embedded device begins with one critical security decision: what software should it trust? Secure boot makes this decision by authenticating firmware before execution. If an attacker replaces the firmware security inside the operating system, or the application cannot help because the attacker already controls the device from the first instruction. Most existing solutions, secure boot, use RSA or ECC. These are secure today, but sufficiently powerful quantum computers could break them. This is particularly important for defense, aerospace, industrial and critical infrastructure products that may remain operational for over 10 or 20 years. Our challenge is therefore to make post-quantum firmware authentication practical on an embedded RISC-V platform while extending the trust beyond boot into running applications. So, next slide. Let's talk about solution overview. So our solution is a hardware-accelerated post-quantum secure boot platform built around the Shakti Yamuna RISC-V processor. On a trusted development host, FreeRTOS and our application tasks are compiled into a single firmware image. That image is encrypted using AES-128 and signed using dilithium-2. After reset, the Shakti processor runs our secure bootloader. It authenticates the encrypted image using dedicated entity, INTT, and accelerators. Invalid firmware is rejected immediately. Valid firmware is decrypted by the AES hardware and launched as a real FreeRTOS runtime. After boot, a telemetry task creates sample device data and signs it using a separately device identity key. The firmware key controls which software may execute, while the device key establishes the foundation of authenticating data produced at runtime. Now, we're talking about our USP. Our USP is that it's a complete integration. So, of post-quantum authentication, encrypted firmware, hardware acceleration, FreeRTOS execution, and runtime data signing in one continuous system. Simply put, we protect the software allowed to run and demonstrate how the software can sign the data it produces.
At the hardware level, our platform is built around the Shakti Yamuna 32-bit RISC-V processor, connected through AXI interconnects to system memory. The secure bootloader is the first software executed after reset, while the protected FreeRTOS firmware is stored separately in external memory. We also model secure key storage within the system to represent eFuse or one-time programmable memory, allowing the bootloader to retrieve the encryption key only after successful authentication. The processor communicates with dedicated hardware accelerators through memory-mapped AXI interfaces. The processor manages the overall boot sequence and security policy, while the computationally intensive cryptographic operations are offloaded to FPGA hardware. The secure boot process follows three stages: authenticate, decrypt, and execute. First, the bootloader verifies the dilithium signature of the encrypted firmware. If the verification fails, the boot process is immediately halted, preventing any unauthorized or modified firmware from running. Only after successful authentication is the AES key retrieved to decrypt the firmware. The application consists of FreeRTOS together with multiple software tasks, including a secure telemetry task that periodically generates, signs, and verifies telemetry data using dilithium. UART provides the external interface for observing the boot process and runtime behavior. The complete platform was validated using cycle-accurate validator simulation, automated performance benchmarks, and repeatable tamper tests to verify both functionality and security.
Right, so now let's come to the results. The first bootloader finds an encrypted image of 98,000 bytes. It performs dilithium-2 verification and returns code 0. Code 0 means the signature is valid. The line signature valid, boot authorized is the first major security decision. Only after the decision does the AES decryption begin. Once decryption completes, the processor jumps to the FreeRTOS. Then we see the FreeRTOS under PQ secure boot and starting FreeRTOS scheduler. The alternating heartbeat and second task message demonstrate that multiple application tasks are actually being scheduled. Finally, the secure telemetry task, the message reading is equal to 0, generates 2420 byte dilithium signature and verifies it on device. The result was pass. So now let's talk about the failed situation wherein the firmware is tampered. So in the second screenshot, it demonstrates the attack path. We changed 1 byte in the encrypted firmware using it had been signed. The bootloader returned an invalid signature results and displayed boot denied. So FreeRTOS never started and the telemetry application never executed. So together, these two screenshots prove both sides of the security property. Next slide. Right. So now we tested 7 hardware accelerators configurations using repeatable automated simulation runs. In the software-only configuration, lithium firmware verifies required about 4.7 million processor cycles. With the required accelerators, we came down to 1.49. This is a measured 3.15 times verification speed up. The most significant individual contribution came from KK acceleration, which reduced the verification approximately 1.94 million cycles, right? And then all 7 cycles configurations return correct verification results. So the speed improvement did not come at the cost of any functional correctness. So we separately validated the complete 98 KB free RTOS payload. Its signature verification are higher because the significant verification required 7.31 million cycles, followed by 3.82 million for AES decryption. These numbers are higher because this is a complete RTOS image rather than a smaller controlled benchmark for reliability.
Unlike conventional approaches, we are combining Dilithium-2 based firmware authentication with AES 128 decryption while accelerating cryptographic operations. This gives us both stronger and better performance. Our primary customers would be RISC-V SoC designers, defense organizations, automotive manufacturers, and industrial IoT companies. With billions of RISC-V cores already shipped and the growing demand for post-quantum security, we believe this is the right time for a solution like ours. At the moment, our project is at TRL4, where we have successfully validated the complete proof of concept using cycle-accurate validator simulations. Looking further ahead, we plan to integrate this accelerator into production, FPGA, and SoC designs. Our goal is to turn this into a reusable security IP that can be adopted in the future RISC-V-based embedded systems. Thank you.
At the end of it, I would like to say that throughout this journey, we had learned a lot about hardware security, computer architecture, and hardware-software co-design. Also, we would like to thank C2S and IIT Madras and Shakti for this great initiative for us to learn and grow so much in this field. Thank you so much.
That was a good presentation by Team 2. Moving on to the next team, to give a brief intro about the problem statement that they faced. Illegal hunting is a significant threat to endangered wildlife, and delayed detection can lead to irreversible damage to the nature. This solution that is implemented by Team Neurobytes from Zeta Wave Tech employs the Vega processors and LoRa technology to identify gunshot sounds in real time. Once a gunshot is detected, an immediate alert is transmitted to the forest officials. To explain more about this solution, I'd like to invite Shankar Narayanan, Guha, and Bani Mitra Kundu to continue with the presentation. Please give a big round of applause for the participants.
Thank you all. So we are Team Neurobytes, and we are here to present our work on ROAR, which is an edge device for acoustic ML. ROAR stands for Real-Time On-Device Acoustic Recognition and Logging System. And this is our team. We are from IISc. Professor Chetan is our mentor, and I am myself, Shankar, Ketan, Bani Mitra, and Guha, and Tanisha are the part of the team. So what we are focusing on is on the illegal poaching. Because you can see like there are many use cases like, the deforestation and poaching has been a long-standing problem across worldwide, and India is also getting affected with that. Because these activities not only endanger the wildlife, but also disturb the ecological balance of forest ecosystems, leading to irreversible biodiversity loss. To and apart from that, the existing challenges with the current systems we face are the visual blind spots, because camera traps and drones cannot cover the full 360-degree angle. And then there is always going to be a delayed response, because like the patrol staff are often understaffed. And the existing solutions also, when you want to stream the videos, everything, it requires high power and much higher bandwidth of the data. For that, we are proposing our solution called ROAR, which is a custom SoC featuring Vega 801051 core with the following configurations. We have a triple mic configuration, which enables acoustic detection and localization, which is a part of the future scope. Then we have an Edge AI classifier, which basically predicts the gunshot against the forest background. Then we have a LoRa communication for long distance communication. And we have a data logging and playback feature. Then the whole system is basically remotely powered, battery powered, and solar powered option is also available. So you can see the 3D model of the system, and this is our system, like basically the top overall overview of the system. Now, coming to the technical implementation, you can see that we are using, we have developed some in-house IPs that you can see on your right side, and on the left side were the IPs that were provided from the CDAC team for this work. So what basically we do is, we have the, we acquire the data from different audio sensors, then we do a feature extraction using MFCC, which is part of a DSP core processor, and then we run our AI accelerator on this pre-processed data, and then finally send whether the gunshot has been detected or not using our LoRa transceiver. Now, what we have done in terms of the technical implementation was, like, we have developed our own accelerator, AI accelerator core, which is a systolic based accelerator, and it can be leveraged for accelerating different types of ML tasks and models. We used communication protocols like UART, SPI, and then I2S for the microphones. For SoC building, we mainly focused on AXI4 and AXI4 like protocols. Then coming to the software, our whole software code was based out of on a basis of interrupt basis, because it helps in pushing the whole system for a low power mode. Because if you use like a conventional polling method, etc., it consumes more power and your processor is always on. Whereas if you go for an interrupt based control, it can really push your system for a low power mode. And these are internal systems. So like if you can show, like this is the enclosed version, but what is sitting inside this is is what you see here. You have an the RT7 FPGA board, and along with that you have like different daughter card, DSP daughter card, and the different mic configurations. Those are all connected to the system. Now, how do we do this? We have like the whole flow of our system is, we acquire data from the microphone, and GPS gives us the coordinate for where the system is placed. These all go to the Vega. Then we do the MFCC computation with our DSP coprocessor. Then following that, the AI accelerator basically does the ML model implementation. And then we send the predicted value to the LoRa transmitter, which says, okay, whether gunshot has been detected or not. And along with that, we are also having an SD card that basically logs the data, whatever data, audio data that is coming in. And these are the salient features of that. Now, this is the demo GUI that we have developed for this. So you can see that the GPS basically tells on which location the device has been placed. And here you can see in the GUI whether, like continuously you can see whether gunshot has been detected or not. And yeah, we have been able to test detections up to 100 meter. And the gunshot model that we are working on, we got an accuracy prediction of around 96%. And we have the reliability of data analysis and post-processing with our, of 80 hours of playback. And the current version runs on for 3 hours with battery pack of 900 milliamperes. And the battery pack is also rechargeable. Now, these are the intellectual property and all. And yeah, the commercialization aspect, we are working with different government organizations and Ministry of Forest Department for further, sending out this product for deployment. And yeah, and that's it, I would say. So we can then play the video. Just call it. Yeah, that's fine. That's fine, we can just show the copies.
You have to keep the mic.
So this we tested near our inside our campus for different forest setups and all. We mounted the system on the tree, and then yeah, you can just see the video. Yeah. And we played at different distances from the speaker. So you can see in the GUI, you are able to see like some data is coming. And whenever we play the sound, it gets, yeah. So you can see it is a detected kind of a thing. Yeah. So yeah, that's from our side. Yeah, thank you.
Thank you for the wonderful presentation. Now I would like to call upon the next team. Most text-to-speech and speech-to-text solution available today depend on an internet connection, limiting their usability in offline environments. The team Ashintya from CARPS AI Private Limited came up with a solution that uses the Shakti to provide fully offline multilingual text-to-text and text-to-voice conversion. The model is optimized with fewer parameters while maintaining higher accuracy and low latency. I would like to invite the team members Shivam Banshal, Ajit Shahani, and Priyansh Bharani. Give them a great round of applause.
Hello and good evening, everyone. So this is Shivam, Priyansh Bharani, and Ajit Sani. Problem statement is that there are multiple sectors that requires real-time language translation, and currently all of the tasks for language translation happen through modern cloud servers like Google Translate, and they are not in India, they are foreign-based cloud servers. So there is a very, very big privacy problem with them, and there is also a latency problem with the API calling. So there are multiple, we have listed some of the limitations with the translation system, that they are not totally offline, and there is a privacy issue, and there is a very expensive infrastructure requirement for those cloud servers, and there is also a very high latency. Next, there is a target user, what we are targeting right now. There is a judiciary problem right now in India. Almost 43 million court cases are pending right now just because of the need of translating them from their regional languages into English for the higher court hearings. There's also international tourism. Almost nearly 1 crore foreign tourists visit India annually, many of whom face language barriers while communicating with transport services, hotels, hospitals, and local businesses. There's also interstate travel and migration. Nearly 1.9 crore people travel by train daily. Over 4 crore people, Indians, work outside their home state, and they face a lot of barrier while communicating with and taking other services. There's also an educational aspect. Government schools and institutions like JNV requires almost 30% of their students annually to travel to other states through migration programs and to study there, which in 9th standard, they face a lot of problems because of that. The solution that we are providing is that an FPGA-based offline multilingual translation system that works in real time, powered by custom hardware accelerator along with Shakti Yamuna processor. So these are some of the innovations that we have done. We have designed totally the hardware accelerated pipeline. We have done precision quantized module execution, and we have done modular multilingual architecture as well. This is the product demonstration. As you can see on the screen, we can do any to any language translation. So in the demo, you can see English to Hindi and Hindi to English. You can select any mode, English to Tamil, English to Telugu, Malayalam to Telugu, any language is supported. Currently, we support text to text and text to speech translation. In future, we are going to include speech to speech and image to speech translation. These are some of the performance benchmarks. So our model takes almost 15 milliseconds for single word translation in a bilingual translation. If it's a multilingual translation, it takes 25 milliseconds for a single word generation. The total power consumption by the SoC is 1.2 watts. Currently, we have supported on the RT 4 languages, and the BLU score for the translation is 18. There are some other solutions as well. Recently, Indian government has taken an initiative by starting Bhashini. It's a cloud-based system, but it's really very, very good. But most of the solutions are like Google Translate and Amazon Translate that relies on foreign cloud servers. So this is our presentation. Thank you.
Thank you. Thank you. Thank you.
Thank you for your wonderful presentation. This concludes the first set of presentation. What an impressive display of talent. The level of innovation we witnessed today is a testament to the thriving ecosystem being built around the RISC-V architecture.
We would like to take this opportunity to wish all the startups all the best in their future endeavors. However, the excitement is just beginning. Day 2 is set to be an even more significant, featuring the final team presentations and a high voltage AI panel discussion. We look forward to seeing you all back here bright and early to conclude this journey together.
Thank you.
Thank you for your participation today. Have a wonderful evening. Thank you.